Hello, hello. Hello, 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 hello.
Good morning. Please find your seats. Come on. Neil, please find your seat.
No time in this computer.
Oh, there. No. Do you want to start now? Start now, it's 9 o'clock.
Yeah. You start?
Yeah. Start.
Okay, thank you. So, I think we are ready to start. Good morning, all, and welcome back for this second morning session on products of IMDIS conference. First of all, I would like to thank our hosts for the very nice evening we had last night in the traditional restaurant. I think we enjoyed it very much. Thank you very much. I am Sisi Iona, and with Helge Hagen, we will chair this second session of the conference. So let me introduce my colleague, Helge. Helge is originally a developer and started at IMR in 1989. During the years in the oceanography division, he did a lot of scientific cruises, working with moorings, mainly collected data about ocean currents in the Barents Sea. Since 1999, for 25 years now, is the head of the data center. Also, he has involved in many European projects, the SeaDataNet family projects, IMOTNET projects, and services like Copernicus in situ data center for the Arctic. Nationally, he is the coordinator of the Norwegian Marine Data Center, National Research Infrastructure, which is serving marine data. Your turn now, Helge, to say a few words.
Thank you. And then Sisi from the Hellenic Center of Marine Research in Athens, in Greece. She is head of the Hellenic National Oceanographic Data Center, just like me here.
Yeah.
We are really colleagues.
Yeah.
Her background is in physical oceanography, expertise in data management, been involved in a lot of EU projects like SeaDataNet and IMONET, been chairing in JCOM and IODE, and the main research activities besides data management is data quality validation and preparing climatologies.
Okay, thank you. So,
Let's go.
a few words for the session. The format, as you have seen in the agenda, will be the same as yesterday. The oral presentations will be 10 minutes plus 5 minutes for questions, except the keynote presentation, which will last 20 minutes, and 5 minutes also for presentations. Let me remind you that you can put your poster over there on the stands, and the poster session is this afternoon after coffee break. So I think we are to begin our session. Let me say that a few words for the yesterday session that we enjoyed. Really, it was very interesting, and we saw the big challenges of how to connect data with knowledge in an easy and in efficient way. Today, we will see what is new in data products in the marine domain, what new technologies are used to process marine data and produce the information and the knowledge that we all need to better understand the marine environment. So I invite now Niels Olaf Handgerger for IMR for presenting us the fisheries, acoustics, and deep learning, our keynote presentation. Niels?
control. Is that on?
Yeah.
All right. All right, good morning, everyone. Yeah, my name is Nils Olav Handegard. I work for the Institute for Marine Research here in Bergen. I don't work with data management or data like most of you guys are, but I use a lot of data. So my background is applied mathematics. I've been working with acoustics most of my career, but I've also been using a lot of data, so I have more of that take on it. And more recently, we've been working with deep learning algorithm on acoustic data, and that's what I'm going to talk about today. But first, why are we doing this? So fisheries management requires data, and I don't know if there's a pointer here. Or? Den översta. Never mind. I could do this without it. So the point is that for fisheries as management, there are two main sources of data. One comes from the fishery itself, and another source of data comes from marine institutes like us. And we do typically surveys, and the reason why I have these two data sources is that one of them is targeting only the fisheries. So if there is a new year class coming into the fishery, we also need to have an idea what's coming in the next few years that is not really visible in the data from the catches. So that's where we come in, and there are two main surveys that we are doing. It's the troll surveys and acoustic troll surveys. And for the acoustic troll surveys, we use echo sounders basically to convert the echoes to the number of fish. So it's pretty simple. So that's what I'm going to talk about today. This is just an example of two acoustic troll surveys coordinated by IMDIS. This is an international survey, so there are several nations involved. You can see the pink lines are the transects, the acoustic transects, and I'll show you the echogram later. I'm sure many of you have seen it before, but I'll go through it anyway. And then the blue dots, that's the troll station. So you do sampling. You also have to also know the age structure of the fish, you have to know the species and so on, which will help you when you interpret your acoustic data. So you can see the coverage is pretty large, and it's a lot of effort that goes into this. So if you take one of the pink lines, which is an acoustic transect, and take a subset of that, it looks something like this. You can see the upper part. It's all time, by the way. So the y-axis is time, but since you know the zone speed, you convert it to depth. The x-axis is also time, but since you know the speed of the vessel, you convert that to a spatial distance. And then you have sort of the spatial coverage of the water column. You see the yellow line at the bottom, that's the bottom. You can see the stuff up in the water column. There's fish schools. There's 3 fish schools in this image. And we are basically summing up the backscatter from that image. And since we know the properties of one fish, we take the sum divided by the 1, and you get the number. I mean, it's not very complicated, really. But what is a little bit complicated is that what is the backscatter that is associated with each species? So in this case, you can see the annotations below. And that is manually done by the people on the ship. And it's a huge effort that goes into this. So you can see the red dot there is annotated. This is a sand eel survey. So that's a sand eel. And you can see the green one in the other part here. That's something else. So essentially, from this particular survey, they have 3 labels. It's background, it's other, and it's a sand eel. Okay? Pretty simple. Okay, so if we look at the historical records at IMR, we have approximately 295 surveys. And by survey, I mean like a cruise every year combined into a cruise series. So there's quite a lot. I think we have, I spoke with Anfinn, I think it was 2 petabytes of acoustic data, which is not something you can put into your laptop. So you need some ways of dealing with an amount of data. And they're all stored, and we have a cold and hot storage at our IT department, so you can access the data. So it is possible to get the data. but it's hard to work with them. In addition, you have the annotations in the same format in the cold and hot storage at our data center. So this is for the more tech-savvy people. We use PyTorch for the deep learning methods. I've been using X-array a lot. For those of you who know how that works, I really like it. And we have also been experimenting with how do we get the data into the models. We have used S3 and SAR, and we use file-based system and NetCDF. So in essence, what we get is that we add all the echograms and labels and everything into X-array objects, and then we use a NetCDF, the ICS convention, on the data. Now, that convention is not really quite fit for this, so we are working with developing it further so it actually works on gridded data. But that's something that is work in progress. But this is all fine, right? This is, if when you get here, you're good. But to get there, I think someone yesterday would, I think you with the images and the videos, right? 80% of the time goes to data preparation. Maybe. I can, with confidence, say that we have way more than that. I would say 95%. From this part to that part. So all the funding goes into cleaning up the old data. And the reason is you have to apply calibration. They're missing, sometimes time goes backwards, log distance errors, aligning frequencies, folder structure changing over time, proprietary data formats changing over time, label data formats changing over time, and that's where the time goes. So it's really, that's this time sink in this. The deep learning model is just install them and off you go. But when you get there, all the annotations and all the backscatter data are embedded in a list of X-array objects. So you have everything available from your laptop. Of course, you can't get all the data at the same time, but you have links to the data. So it actually, a system that links back to the data on the storage system we have. So that's what we did for preparing what we are doing on machine learning and acoustic data. And it took us quite some time to get there. So if anyone have any advice or experience with any of these technologies, please let me know, and I'm more than happy to hear your experience with it. Machine learning. There is a lot of things going on machine learning at the moment, and it's moving very fast. But really, I mean, the big change happened in 2012 for the Krzyzewski paper for images. And since acoustic data looks like images, we are using image-based systems. So convolutional neural network works really well on acoustics. We started playing with these methods a few years later. The Kjetil Maldes in the audience led this paper on machine intelligence, the data-driven future of marine science, where we looked into all this different technology, not only on acoustic data, but that was my part of it. ICS started the VGMLearn, which is the working group on machine learning in marine science. That has now into its second term. And that workshop, or the working group, did a review on machine learning and marine ecology. And it gives a pretty nice overview of the different methods that have been applied, what kind of fields it has been applied to, and the different types of AI. So there are, you could say that you have deep learning is the heavy hitter, which requires a lot of data to be trained. Then you have more simple machine learning methods, and AI is encompassing all of this. So I think the nice thing about the deep learning part is really that it generates its own features. For those of you, I don't know if you've been working with these things, but typically the traditional machine learning methods require you to extract the features yourself and then apply some kind of machine learning on it, whereas the deep methods go directly on the raw data and extract its features itself. And the idea is then that the machine is better at generating the features than we are. You can see the figure to the right. That's the overview of all the papers that we associated and then found related to this field. And the one upper right is active acoustics, which is my field. So approximately 60 papers on this out there. We also tracked the different methods and how they changed over time. And you can see the different sort of main methods that has been used over time in marine science. And you can see that there are some patterns in that figure. And typically, what you see at the lower part of random forests and convolutional neural network is really on the rise. So that's something that happened over the last maybe 10 years. So random forest is a method where you can use when you generate your own features, and then CNNs are typically when the machine generates the feature for you. So back in 2015, this is the UNET paper came out, and that is a very nice paper that's been used a lot since. I made on purpose, I have not been picking up the latest, most fancy papers, but because I don't think that's the key thing. I'll come back to that a bit later. So this is images of cells, and then you label the cells. You can see the different colors for the different cells, and then you see the predictions. So you train a model that can do this prediction for you, because this is very, very time-consuming to do by hand. One trick you have to do to make this work is they have to penalize. You see the one to the image to all the way to the right. You have to penalize the border between the cells, because you really do not want the border to be part of the cell, because then they are merged. So there are some tips and tricks you can do, and it's a pretty nice paper if you're interested in image-based analysis. And the other nice thing about it is what we call a fully convolutional neural network. So the size of the image doesn't matter. There is no fully connected layers in the end for those of you who are into machine learning. So you can have a big of an image as you like, which suits the acoustic data quite well. So the architecture, how many of you have been using convolutional neural network or know how it works? Yeah, so I'm thinking maybe I should not go into the details here. But the key thing here is that you can see the input image and the output image. So the input image is the acoustic data, like I showed you earlier, and the output image will be the predictions. And it looks like this. So you can see the input image is the echogram, and you can see you can see 4 layers of data, which is the different frequencies of acoustics. Because the different organisms have different acoustic properties, and then if you have several frequencies, then you can use that for the discrimination. We train it on the annotations, like I showed earlier, and then you can see the predictions at the bottom. The figure to the right is what we call a precision recall curve. And really what it means is that if you take your prediction and you threshold it, everything above the threshold is Sandhill, everything below is not Sandhill, right? So imagine if you pull that threshold upwards, the pixels that are predicted as Sandhill is fairly likely that it is Sandhill, because you are very strict, but then you lose most of them. If you lower the threshold, the other thing happens is that everything, you will get all the Sandhill schools, but you will also get a lot of other stuff. So there is a combination between the precision and the recall, and you really want to be in the upper right corner where you have high precision and high recall. And in some of the years, we do pretty well. We trained the algorithm data from 2010 to 2016 and used the blue ones are the predictions. The green dot is the traditional feature extraction methods that we used before. Now, this is all fine. Of course, there are some issues with these methods. And this is one of the problem that we are facing. It's highly imbalanced. So yeah, we have 2 petabytes of data, but only 0.2% contains something that we're interested in. And we can see in the upper layer it's probably a plankton layer. And the problem is the plankton looks more like Sandhill than background, and the network thinks it is Sandhill. So you need to fix this somehow. So we've been working on how we can address highly unbalanced data sets. And it's quite simple, really. You just take your Sandhill patches, you look for something that's similar that is not Sandhill, and you use that when you train. So you pick the background samples that looks more like your foreground class, and then you train it. And it works. So it's not very complicated, but it's very important that you are very careful when you train these networks, because it's not going to work out of the box. And I think this goes for most applications I've seen in using these methods. We also work on what we call weak labels. Sometimes we don't have the pixel that is associated to a species, but we have a layer like this. This is 30% herring and 70% something else. And then how do you use that kind of information to train networks is something that we are working on. You can also use semi-supervised methods where you cluster the data. You say, this looks like I don't know what it is, but it looks like something like this. And then you bring in your labels later. And that improves the training by quite a lot. You basically use the structure in the data. And that's something can be used when we don't have labels as well. And this is a case where we've been working on methods where you do not have labels. So this is fully unsupervised, and it's not working perfectly yet, but I'm sorry. You can see the lower image. So these blobs are being found in the data. They pretty much look like the sand eel. You have the problem with the plankton layers at the top, but this is trained without any labels at all, because the labels are really the key challenge when you work with these methods. But this is all fine. So we've been playing with this data, right? It's really fun, by the way. But how do you use it? And that's where the machine learning engineering for production comes in. And this guy, I don't know if you know deep learning AI, but it's a really nice. Just go on YouTube and take a look. It's pretty good. And he has a series on machine learning for production. And this is something that I think is very important, and I think it's especially important for your community, is that you can have a model-centric view and a data-centric view. So the model-centric view is that you have some kind of, it's typical Kaggle contest if you've been involved in such things. So you have a data set and you throw models at it, and then the winner, gets the prize and everyone's happy, right? The other way of thinking about this is to say that, well, maybe we can change the data. Maybe we can improve the data quality. And what happens then is that when the data quality improves, most model works fine. And it's really about the data. And that's what we see. That's why we spend so much time on the curation of the data. You have to work with the data. You have to, you have to be nice with them. Data are not static. Because when you see new things, you have to address it somehow. Of course, you keep your raw data, but then you have to work with the data. And there are many examples. I could spend the rest of my talk about that, but I won't. But it's really important. Data is more important than the models. So what we did for putting this into production, we have this. You can see the upper right is it's a program, the software they use on the ships when they do this manually, and it's pretty boring, to be honest. It takes really a determination to do this year after year. So we just interfaced our model with that, and then you can get a prediction like you see on the left, and then they can edit it and then see if they're happy with it. So it improves the speed of the annotation process. Another way of thinking of putting things into production is to automate it completely, and you should be a bit careful. You have to have checkpoints if you do that. But that typically is the case when we are now moving from research vessels to USVs. So we are playing around with USVs, and we are deploying the algorithm on the USV. And that is a little bit tricky because we don't have an IT guy on board that can do this installation. We don't have anyone to do the annotations on the USV, obviously. Otherwise, it wouldn't be USV. So how can we take this model and deploy it? And this is what edge deployment is all about. This is a little bit to side what I'm mainly working with, but you have a processing pipeline and you want to run it on the sounder in this case, which is the USV that we are using. So we package things up in Docker containers, but then someone has to run it. So we've been working with Kongsberg Maritime on this, and they have like I don't know, this is way beyond me, but they have some fanciness that we just provide them with a Docker and they run it. And that's a very nice way of separating the concerns. And I think that's something we can also do on historical data. So we can just give, so the domain experts provide something. It could be a data cleaning method or anything, and we provide that for the data centers and they can run it. Because they don't have the domain knowledge, so you have to have this connection somehow. There are other ways of doing it, but this part is hard. I think I said I've spent 95% of the time preparing the data, 5% training the models, and not enough time to do this. So I think this engineering aspect of this is really important. And it's difficult. And maybe one of the reasons why it's difficult is this. So, I mean, you can read it yourself, but this is a quote from the Surely You Joking, Mr. Feynman. It's a pretty nice book, actually, if you haven't read it. And the problem is that you play with the computers, and it's because it's fun. And I've been doing that for many years, and I think it's fun. I like it. But the problem is you may lose track of what actually you are trying to solve. And if you not connect very closely with the users or how it's going to be used, I will probably spend the rest of my career playing with neural networks. I mean, it's fun, but it's not useful. So I would like to acknowledge CRIMAC and the Norwegian Research Council for funding and the RECIFE program, and that's it. Thank you.
Very much, Niels, for introducing us this very interesting approach, which is actually the future in this domain. And also for highlighting the importance of good data that you need for your models, because without that. So, questions, please?
Thank you. I'm a big fan of Feynman. Actually, that quote on playing ties into my first question. The story you're giving about it's easy, you just train, you identify the wrongdoings, you label them correctly, and you then feed the plankton problem. But was that an ad hoc thing, or is there also a systematic? It sounds like you're starting having a dialogue with your AI, right? Yeah. You say, oh, well, you got this wrong, now you have to fix it. But does it help you to isolate the things they got wrong, or is there a systematic approach to this, or is it really serendipity where you say, oh, we stumble upon your error, so now we go for it?
Well, I mean, what you do, you look at the precision recall curves, and you see there is a problem, and then you try to improve it. So you have a metric that defines whether it's improving or not. Okay. So based on the metric, then you try, okay, here's something wrong. What can it be? And then you have to dig into it and take a look. Yeah, there's no way, there's no magic way here, I think. But maybe there is, because you have the metric, so you know that it's going
so at least that's it, part of systematic is checking on the metric, right? So you have a way to identify false positives or false negatives. Yeah, okay.
Given that the labels are correct, right? So that comes back to the data quality again. If the labels are wrong, your metric is also wrong. So sometimes that is the case.
Messy.
I mean, data is messy, and I guess all of you know this. Yeah. But so there's no magic in this. I think sometimes we just have to sit down and do the hard work and clean up our data. Honestly, it's just there's no magic to this. Yeah. You have to have domain knowledge. You have to understand what you're doing. And you have to work very closely with the data centers to ensure that the value you add to your data is fed back into the data system.
Yeah, probably another case where engineers and scientists have to collaborate on.
Yes.
Yeah. My second question might be way too technical, but when you're showing these Docker instances running, and the magic that people do this for you, but part of the magic must be good access times to the actual data.
Yeah. Oh, yeah.
And you have any idea on how that is? What magic is going on there?
For the prediction step is not a problem, because you have a ping repetition frequency of 1 per second, so the data that comes in is not very large, and it's not a big problem. The challenge with access time is during training, because imagine you have we don't train on all the data, but on one survey is somewhere between half and 1 terabyte for one survey. And you want to sample randomly inside that image, right? And then you need random access to your data, and you need methods that could do that fast. That's the big problem. And then this is also a bit detailed, but then you have to, there are tricks you can do with the chunk sizes of the SAR files, so you can sort of chunk it into smaller chunks and then make sure that, so you first your sample, and then you can sub-sample within your chunk. This might get a little bit technical, but you asked for it, so that's sort of the, but if anyone has experience with that, I will be very happy to talk to you, because that's the bottleneck.
So But the key element is ZAR files on S3, right?
Sorry, that.
ZAR files on S3.
That's what
where
we've been using. I like it because it's pretty, but I'm concerned about the access speed when you train big models. Yeah, good.
Is there any other question?
Hi, Björn Bakkerberg from Deltaris. Thank you very much for a very interesting presentation. You've talked a lot about data quality and the importance of that. I'm wondering if you could say something about data volumes. I'm thinking in particularly about situations where we do not have a lot of data and how that affects, for example, accuracy, or what are the ways to overcome the ability to predict situations where we do not have a lot of data? And
okay. If you don't have a lot of data, I mean, look at it. If you look at it this way, if you use a deep method, there's a lots of parameters. There's thousands of parameters, and if you don't have enough, if you have 1,000 data points and 1,000 parameters, you know where it goes. So, if you want to train a complex model, you need large amounts of data, and you need data that actually has what you're looking for in them. So there is no magic, but I don't know the number of sort of this data sizes and stuff like that. But I think the main challenge is labels. So we've been doing this for, similar to you that you know, coating the fish on the images. So we just simulated it. So we have a nice background, we pasted in fish, and then we train the neural net, because then we can have as many as we want, we just simulate it. So if you have a very limited data set, don't go too fancy on the models, I think.
I was thinking about hybrid modeling, like for example, using other IMDIS products from a physical oceanography perspective.
Okay, but then if you have, I guess you have pretty large amounts of simulated data, right? Then you could just simulate more, and then I don't know. Yeah.
And continue in the coffee break, because time is,
Sure.
very limited. So,
Thank you.
Yeah, next speaker is Charles Chopin. Interpolation of plankton continuous recorder data using a neural network technique.
So I guess after yesterday's session, I cannot take more time than the 10 minutes, otherwise I will be, I'm sorry. Okay, let's go. So we'll talk about interpolation. So a small outline of my talk is this one. So you have in green the data set. As we see just before, it's important to talk about the data. We'll talk about the method. It's called DINCAE, it's our tool. And finally, our goal is interpolate the data with DINCAE. Pretty easy. I want to start with this quote. I really like it, and I will ask you to try and find who said that. Some of you know him, others not. Before you could apply all your artificial intelligence algorithm, I had to pull real intelligence to prepare the data. I really like it, and it makes sense. It could be the conclusion of my talk. How it all began. We had Pierre, a scientist from it's his real name, from the MBA in UK. He said, guys, could you create graded maps from my data? And as in Liège, we always create graded maps in interpolation. Say, yes, sure, send the data. And Pierre said, okay, here you go, get the data. I was, oh, why do I say that? This is the data. I said, 1 month on data. I said, but it's real. And I said, whoa, we need to create graded maps for that. We'll manage it, but how? What are these data? They are called CPR, Continuous Plankton Recorder. I could talk half an hour about that, but I will just spend 30 seconds because it's complex. But what is nice is that for many, many years, since 1931, they used the exact same method to get the data. So it means to explain, to study climate change, it's perfect. So it's a device that is used in ships of opportunities that get you, thanks to human intervention, you can get a counting of different taxa, different species. And that's what we will work with. You have the link here, CPR survey, it's very nice. So this is the full data set. It spans the 58 to 2020 period. We have about 250,000 observations in total for all this period. And what we get the data, position, time, and abundance of different species. If we represent this kind of plot, it's an X-bin, we count the number of data we have. We have a lot of problems because we have many data in the black areas like this. And the yellow-white area, it means we don't have a lot of data. So it's very heterogeneous. In terms of time, it's the same. So you have the full-time series, number of data per year. you see it change a lot. So it's lots of difficulties for us. We will focus on two of these nice species. You have the name there. I don't, again, spend detail on there. They are studied a lot. It's nice because if they are studied, we know the behavior and we can validate a result. But the last line is the most important. We have an influence of the seawater temperature and the bathymetry on this distribution. So it means we can maybe use that in our technique. They have the two of them left. We have one of the species, they right, the other one, they have totally different distribution. So yeah, it's nice to see that, yeah, they are not the same because they are driven for the temperature. The tool is called DINCAE. If you know the group in Liège, all the tools, they start with D. DIVA, DINOEV, DINCAE, and say why? But DI is data interpolating. Okay, we interpolate data. The C is convolutional because this technique is using a convolutional network and works on subset of data and train and get the local feature. That's what we want to show. In the AE, compress, decompress based on the essential feature on the data. So the technique is quite heavy to understand. You have the code because the code is available on GitHub and the Zenodo link as well. Another book, I don't know what it is. Okay, there was some QR code that are not displayed. I don't know why. So okay, do we have the links? So there are two papers. The first one, 2020. It was the Python version, working quite well with TensorFlow, and then we switched to Julia in 2022 in this paper. Julia is not a new language now. In the past, we were saying it's a new language, but it's the language that you use for programming. If you remember, 6 years ago, we had the harder, better, faster, stronger when I was presenting Julia language, you know, all the Daft Punk songs. So it was really what summarized the language. And now I would say Julia is really faster and much more mature. It means we can install it. It's really a pleasure to install it to any machine. It works well. All the package management is fine, so we like it. And plus, we can do GPU computing and train our neural network. First result that we got, and as I say, it didn't look that nice. It's a mess, really. We have many problems. You can see all the problems. You don't need to understand the data to know it's not good. We have stripes. The gray, we have negative values. So how do we get negative abundance? We cannot do a lot of problems. So the issues are not that. Negative value, anomalous, need a boundary, stripes. So got a message from Pierre, the guy that provides, guys, what are you doing with the data? I say, okay, we have time, we need to do something. What do we do? Solutions, a lot of solutions. We apply a transformation on the data, a typical transformation logarithm, and we help regularize the distribution. So it's done a lot in this field. We enlarge the domain to avoid the problems at the boundary. We perform multivariate analysis, I will explain later. We add a smoothness constraint in the cost function, I will explain later, and tune the hyperparameters. Why do we do that? Unwritten variables in the neural network, up to now, we just input, we just feed it with the tracks, the very poor data set. And we think, okay, but these species, they depend on the temperature. We have information on the temperature. We have climatologies, we have models. So let's put that inside the neural network. We put the sea surface temperature from a Hadley data set, monthly product, good resolution, good coverage. Let's do it. We have the bathymetry, GEPCO. If we go to final resolution, immuno bathymetry, well, we can put that because we know the species depend on them. If we have other species, you can put chlorophyll concentration. So we have priori knowledge of which variable will help to improve the results. A little bit of mathematics, always one slide like nobody understands, even me, it's like, okay, let's do it. So we have the cost function looks like this at the beginning, and what my colleague Alexander did is add two terms, and you will see this Laplacian operators. What he will do is we'll add a new constraint to the cost function so that the result we get are smoother. We get less stripes, less small scale variability. We can play with this coefficient, so we'll see directly how it influences the results. Small coefficients, that's the kind of result we get. I improve the coefficient, I multiply by 10, and what it does, it's smooth. So we have these extra parameters to optimize to find a better result. I will explain how I optimize later. See, if we smooth too much, we don't get anything, and we know it's not good. Some results. This is the climatology, the seasonal cycle from this Calanus species. So you will see how it develops in space and time. So April, May, June, July, etc. So this kind of evolution makes sense because we know the data. Pierre can confirm and say, okay, yeah, it makes sense what you observe. You have this region with no data at all, it's good, no value at all, it's good, so okay, we're happy. For a given month, let's say April 2015, this is what we obtain, and I always want to show the data we had for that month. So it's nice that the neural network can get feature even with a very, very sparse data set. What else? Comparing the observation with the data to perform some kind of validation. Let's keep that. Time series as well to see that we are able to reproduce the seasonal cycle. That works. And the other species, Calanus helgolandicus, which has a totally different preference in terms of temperature. You see that the kind of result that we get, again, they make sense in terms of what we know from the species. Tuning hyperparameters was the worst part because we have how we do. Basically, we do cross-validation, remove some parameters, reconstruct where we have removed data, reconstruct where we have removed the data, and check if we can get closer to what we have removed with the reconstruction. The problem, yeah, there is a problem. We have about 18 parameters to optimize. If we test 5 values per parameters and do all the combination, a typical run takes 2 hours, and you see it's too long. We cannot do that. So how do? We select some of the, we select some of the parameters that we want to optimize. Number of epochs, learning rate, Laplacian penalty, so the smoothing parameter I've been showing, and test random set of value for this and the rest of the parameters, the 15 other parameters, we keep them at a reasonable value. It almost ends here, so Pierre say, okay, it looks good, we shall publish the result. That's what we're doing now. We're writing the paper, hopefully submit it before the deadline, end of June. And also I say, okay, but we can represent the IMDIS. You say, yeah, go to IMDIS. So that's why I'm here, in fact, because we say the results were good enough. So I'm here. Conclusion, neural network technique could create realistic monthly gridded fields. That's nice to know it works even with this data. It was obviously necessary, mandatory to optimize, to tune the hyperparameters, otherwise it's a mess with all the stripes, etc. Adding the environmental parameters, variables contribute to improve the results. 30 seconds left. I have maybe a small word to say about FAIR, because FAIR, we always talk about FAIR. I like the R especially because we say reusable. In my case, I always say the R is reproducible. What I want to do is that anybody can use the code, the same data, and the notebooks that show how to use the data with the code. So we provide access to data, software code, notebooks, intermediate data sets, so normally anybody should do the same if they have a good computer. Future work, white in the paper, and okay, I need to show who was the guy telling this nice one. It was Peter Herman from Delta Res, and I think he's right. The interest is inside the data, not only the method. We need to focus on data. Thank you.
Questions? Any questions for Charles? One.
Mark, okay.
It's not on? No, it's on.
I would hate it if you don't get a question. If you have that little data to work with, I think there's this typical reasoning that, well, procedure in artificial intelligence stuff, where you say, part of the training data, I'm going not to use it. I'm only going to use it to verify my. Do you have the luxury of doing that if you have so little data? Did you do it? Did you have part of the data set aside to then verify if it could predict real measurements, or?
Yeah, we remove 10% of the data.
Okay.
And the thing is, we could remove individual points, but it doesn't make sense because as the track has quite fine scale resolution, if you remove only one single random measurement, you have the measurement at the site that can help reproduce. What we did, we remove 2 degree by 2 degree space, and then reconstruct this 2 degree by 2 degree from the data and see if it makes sense.
Yeah.
It has, so we validate the method, otherwise it.
Well, you need something to verify, but if you have so little to go by,
Yeah.
it's like cutting an arm off. Well
Yeah,
done,
exactly.
thank
Yeah,
you.
yeah. So we did. Yeah, thanks.
method can be applied in other regions of smaller extent, because you mentioned that you needed a larger area to do that experiment.
We can do this data set. I think it was nice to use on the North Atlantic because it makes sense with the temperature distribution. It's really driven by the temperature. So training the model on this large domain, I think it's much more better than a smaller one. But of course, if we work with different variables, not taxon data, but something else, we can do small.
And I suppose for chlorophyll, you can use it with greedy data as input, not only this kind of distribution.
Yeah, okay. Exactly. This was the first time we use it with in-situ data like this. Normally it's done on satellite data, sea surface temperature, etc., to recover the clouds from the data. But this was the first test. That's why we didn't know it was going to work or not. So it was nice to try.
One last 30 seconds.
Charles, I was wondering what's the difference between DINCAI and DIVANDI. It's DINCAI also using environmental variables to do the interpolation, or not really? I didn't understand that part. Thanks.
What the two methods have in common, they work on based on cost function. The cost function, I mean, to have constraints like smoothness, closeness to data are taken into account, but the solving is different. One is the you need to find the minimal cost function with a differential method, DIVANDI, and this one you find the minimum with the neural network technique. So the technique is different, but let's say a large view overall the cost function is the base of the two methods, but they are totally different in the way you solve it. So that's why they have different capacity. What we've done here with DIVANDI, we cannot do it because we don't have enough data. So, yeah.
Okay, so I think we can proceed with the next presentation from Anna Simpson from Aachen University, who will present us the compiling of fair CI score data from a user perspective.
Yeah. Oh, okay, it works. Hi, my name is Anna Simpson, and I'm a PhD student from RWTH Aachen University, which is in Germany. And in this talk, I'm sharing my reuse perspective with you of compiling CI score data sets. So how I started to reuse data was in the frame of my PhD project, for which I implemented a physics-based process model for modeling sea ice evolution. And at that time, my supervisor gave me some ideas on how to continue with the model or how to improve it. And one of the ideas was to include sea ice core measurement data from that are available on data repositories. And we thought, since these data repositories are aligned with FAIR, that it would be easily reusable and quick. So I started to get a broad overview on what kind of sea ice core data is available, and some of it is listed here, next to a picture of a sea ice core. So it is, for example, the salinity or the temperature and the sea ice thickness. And then I thought about reuse scenarios for my sea ice model. So one reuse scenario could be, for example, the validation of this multi-phase, multi-physics process model. And for that, I would need data from different locations, for example, the Beaufort Sea or the Weddell Sea. And for reuse scenario B, I thought about training a classification algorithm for the development stages of sea ice that could be, for example, old ice or first-year ice. And then it would be interesting to see how the model data would be classified in this classification. So now I introduced to you these reuse scenarios, but my reuse scenarios are very specific. So I have very specific requirements for the data that I need to feed in the model or like in the specific scenario. So for scenario A, I have, for example, inputs that are the salinity and the temperature and the solid volume fraction of the ice. And there I have specific constraints, for example, a specific resolution unit, or it has to be below a certain measurement error to keep the uncertainties low. Then I need the salinity of the seawater for accurate boundary conditions. for scenario B, it is especially important that the water body and the development stages follow some specific naming, so it's not a cross-class use of names. So I need a database of all of these elements in these reuse scopes. I call them reuse scopes. And yeah, so I thought, let's compile data sets that are available. An intuitive approach of compiling these data and searching for these data is I saw it as follows. So data sets on these data repositories such as the IMDIS, Pangea, or Zenodo provide these data, or I thought they would provide these data sets, and it would be easily combinable because they may have some structural they may be structurally identical so that I can easily combine them. However, the first round of search revealed it is not that easy, and it is difficult to combine these data because they are very heterogeneous, and the data sets, of course, do not best reflect my reuse scenario, but the data collection. So, but I still didn't gave up, and I worked on a strategy to do that. So I followed a reusability targeted approach for my scenarios and created an enriched CI score database that I call resize. So I started to search for data, and there I had some challenges. For example, that the data that are associated with one CI score are distributed across data sets. And then I could also look into articles where I found, for example, the accuracy of the salinity measurement, which was not available in a data set, or the names of the water bodies. So this kind of matching that I did for each of the cores, I call it element availability matching. So one data set provides me some parts of the reuse scope, some of the elements that I was looking for. Then I look for a second data set where I found more elements. Then I looked into articles and reports and into instrument manuals to fill up all these elements that I needed for my reuse scenarios. And then I continued with the next core. So while searching for the data, I also observed some, I had to do some plausibility checks. So one was, for example, that data sets are redundant on different repositories. This is one from the IMDIS, and this is from Pangea. And the data is the same, the coordinates are the same, and here in the salinity you see it's also the same data, just with one extra measurement here in this data set. You cannot see the mouse. Oh, I'm sorry. Okay, but there's one extra one. And another problem is that, for example, the accuracy was exaggerated. And that, for example, there are inconsistencies. So here was the ice thickness given with 0.43 meters, but then the measurements went up to 0.85 meters. So I collected all these data sets per CI score and sampled them. So in the next step, I technically combined them, everything that I found, and I created one YAML file per CI score. And what I want to raise your attention is mainly this comment section. This moved a little bit. Where I refer to the figure where I've taken this information from, then excerpts from an article, for example, and things that are changed, like if I change the unit and if I change the accuracy and so on. So it's very manual. I did this like a lot of copy pasting and so on. And I also always share the GUI in each of these properties, for each of the properties. So in the next step, these YAML files can then be compiled for the database. And so this is an overview on the availability of the different elements of the database. So here on the y-axis, you can see all the YAML files or all the CI scores on the x-axis, and on the y-axis, you can see all the elements or properties. So if it's dark blue, then it is available from a data set. If it is this little bit lighter blue, it's from an article or a report. If it's this color, it's from a manual, and if it's yellow, it's not available. So what is interesting, I think, is uncertainty is very important for me, but I could only find the accuracy of the devices in the data set almost never, except from one. I can't find it right now. What this trace, oh, this doesn't show as I wanted. Okay, generally, wait, does it maybe show now? No. Okay, it doesn't matter because if you are interested, you can check it in some extra source that I provide at the end. So this is one path of one of this YAML file. This YAML file here, so what x-axis is again CI scores or YAML files, and this YAML file here with this here at the top gets data from 3 data sets, from 2 articles and reports, and from 2 manuals. So it reveals how the data is stored also by the people who collected the data. So now with this I have consolidated all existing CI's data that I found, but I also did some automatic enrichment for some of the elements. For example, the spatial resolution, the CI's development state, and the name of the water bodies, since they were not following these controlled naming that I wanted them to have. So the resized database is real, and it is also publicly available in the interactive Mosaic Web ODV provided from AVI. So on the top, you can see all the locations of CI scores, and here are all the on the lower left are all the salinity data from CIs, and on the lower right you see the development stage, for example. So in summary, what did I do? I used original sources, I used data sets, I used articles and reports and manuals, and additionally these nomenclatures and controlled vocabularies. I went through all 4 steps that I just went through, like the formalization of the reuse perspective, the plausibility checks, and the technical combination. Then I consolidated all data in YAML files and developed this resized living database where each YAML file for each core. Then I continued with the automatic metadata enrichment, and the following database, it's a resized tabular database named here, is then exported to Mosaic Web ODV, or I also created I also uploaded the database on Zenodo. I had to split it into 2 parts because of different licenses of the original sources. So if you're interested, you can scan the QR codes and see, for example, the lower left is the correct version of the plot that didn't work properly. Thank you.
Interesting presentation. Are there any questions for Anna?
Thanks a lot. It's a very good thing to showcase the data use and all the work that goes into utilizing heterogeneous data sets. You've done a lot of work in improving the quality of the data you've fetched. And I was wondering if there's any mechanism for you to feed back that information to the data sources you got the data from. The ideal place to make corrections, if there are general corrections, would be in the source databases. Is other that kind of mechanism in place to give that feedback to them?
That's a good idea. Actually, I was mostly looking, of course, focusing on my reuse scenarios. So I didn't think about it yet, but I can try to reach out to Pangea also and tell them here's some accuracy issue, for example.
Okay, thank you. Other questions? I think no. So we can proceed with the next one.
Okay. So the next one is Alexei Missionov, 2023 release of World Ocean Database and the World Ocean Atlas.
Good morning, everyone. Thank you for inviting me and giving me opportunity to talk. We are working on World Ocean Database for quite a long time, and we're trying to report our achievement, our development on the IMDIS conferences from time to time. So I'm doing it for the third time already, starting in 2008. So we are still on the ANAC presentation. Let me switch. And mine is number 25, okay. So I'm working at Silver Spring. Before it was NODC, now it's a part of NCEI, which stands for National Centers for Environmental Information. Come on. Okay, good. And here we are. It's a team of colleagues who works on this topic, I would say, for about 25 years, and I hope you all know what is this, and you all use it from time to time. So I'm glad to report that we just released version 23 of World Ocean Atlas and World Ocean Database, which are big next step of the collecting data. And as you all know, maybe that the World Ocean Database is a part of international efforts. It's supported by UAD, IOC, and other entities. And also the International Quality Control Ocean Database is like a part of it and a source of it. So Simone will talk about it later today before the lunchtime, so I will leave this to her. And our World Ocean Database have data for quite a big chunk of time, starting from second expedition of Captain Cook on Her Majesty's sloop Resolution in 1772. And we have 3 stations in the database from that expedition. So you can see the cruise report map and the data dump from World Ocean Database. And the most recent data we have now, it's from Argo, a handful of data collected in March. So we have it already loaded into the database, and it's available. So everything is available online, free of charge, of course. So we are collecting data from many countries, and at this very moment we have data from 96 countries, and those pie charts shows the distribution and contribution of each country, and all data and major data types, CTD, XBT, gliders, and floats. So you can take a closer look later, because I have not much time. And since we are in Norway, I prepared this slide. And Leslie, it answers for your question if we can easily separate the data from different institutions, different countries. So it's pretty easy. So here I'm showing the Norway data over the 2 centuries. This one being the data collected during Fram expeditions by Nansen and Sverdrup. So you can see first voyage to the North Pole, and the voyage around the Greenland and Labrador Sea. And the next 3 maps, it's first half of 20th century, second half of 20th century, and the current century. So you can see Norway is pretty active collecting data, and the color codes, it's the amount of the profiles in 1 degree latitude, longitude box. So we are very grateful for Norway to submitting those data. And looking over the time, this is how World Ocean Database was evolutioning, growth. So we see we have more and more data, and the World Ocean Database have data from 11 different instrumental platforms, and for 46 different parameters. So here you see on the very 2 latest column, it's a World Ocean Database 23, and the last one, it's a current situation. So we're making an update every 3 months, so those data the data keep coming, we keep processing them and putting them online. This is an indication of how the inflow data dynamics is changing. So we can see that standard instrumental platforms is, I would say, in some decline. Maybe we don't receive all the data, but you see the CTD, OSD, XBT, and MBT the data flow goes down. And for the new advanced platform gliders and floats, those data flow reach some plateau. And now we're receiving those steady stream of the data from those new instrumental platforms. So you can see here the time scale development of the different instrumental technologies with the rising and the declining of the instrumental technologies like MBT, XBT, and now nowadays last decade it mostly gliders and floats. So which are orange and purple. Okay, another example of the data coverage evolution. So now we can have the data almost covering almost entire globe with example of the Argo profile. So here on the left, yes, is 2009 version of World Ocean Database, and the right is the current one. So you see the floats now covering all the data, all the World Ocean, and note the red color on the left, it's more than 20, and the red color on the right, it's more than 100. So this is, again, it's a amount of profiles per 1 square degree box. So this is another example of data coverage evolution for different instrumental platform. On the right side, it's gliders. So you see in 2009, it was almost no gliders on the database, and now we have plenty of them, mostly from European EGO glider data repository, from IOS, United States, and from Australia, IMDIS. They are very active here. So we are receiving now about 250,000 profiles per year on the gliders, about 30,000 per year profiles from instrumented animals on this one. So you see this French people being very active, and the States also being active here on the northern part. So those data collection pretty active and going steadily over the time. So now maybe you all know, and you all can construct the similar box diagram with your databases, but this is how the World Ocean Database, I wouldn't say organized, it's activity for preparation of World Ocean Database and connected products. So as you all know, we're receiving the data all the time, and it's from all around the world, and this very little arrow, under this arrow, it's a lot of work behind it. It's a data ingest, data quality control, data conversion, quality, duplicate check, and so on and so on. So before data come to World Ocean Database, it's a lot of activities. So we assembling those data, we making quarterly updates every 3 months, and they are published immediately. And we use these quarterly updates for generate some products which are important and which are in use, I hope. So it's ocean heat content, ocean salt content, sea level changes. And we also publishing the quarterly updates of these parameters. And they all are in public access. And from time to time, usually about every 5th year, we preparing the major release of World Ocean Atlas, which contain several volumes like temperature, salinity, oxygen, nutrients. So last year we were pretty busy assembling World Ocean Atlas 23, and it also goes to public access, and it's all now accessible. And another very labor-demanding process, we're doing a high-resolution climatology now for about 10 years already. So some area of the world ocean are now covered with pretty good data density. So we selected those area and created climatology is not only on 1.25 degree as World Ocean Atlas, but we're going down to the eddy resolving resolution of 1/10 degree. So I'll show it a little bit later. So, and everything we are doing, I hope, going to you guys, and you can use it for your papers, reports, and present to conferences. And also, I believe, as everyone here working with data, we have some issue with IT, some problems, and now we're going to the cloud, and it's another, kind of germs. So we're doing this, working with, all those EC2, C3 buckets, and all this stuff, funny stuff, which we're not familiar with yet, but we're going over this way. So during these years, so I would point out that the first version of World Ocean World Ocean Atlas came out in 1982 by Sid Levitus. And since then, we've got 9 releases of it. So it's all here, and it's already 42 years of World Ocean Atlas existence. So. And now the latest version, we have 7 decades. And below here you have the maps from the very first version, and those are now current ones. So first of all, what I like very much is we switched to Robinson projections, which I like a lot more than previous Mercator. And we have 1 degree and 1/4 degree, 7 decades, as well as all data. And they also, I was repeating it once more, it's freely available, free of charge. And here in the yellow box, it's a citation of Sid's paper in 1983, where it says, can you read it or not? So the World Ocean Atlas available for $11. You can put your orders there and there, and the data on the magnetic tapes available for $110, so you can buy it. Now you don't have to do it, you just go and download this. So aside from analyzed fields, we also publishing include the World Ocean Atlas statistical fields. We have statistical means, errors, standard deviation, data density, and all those statistics which we usually produce for World Ocean Atlas. We also have oxygen, silicate, phosphate, nitrates, and another product which I mentioned already is ocean heat content for the last 50 years, and we switched to monthly content, not only for quarterly content. And we have this ocean heat content geographical distribution. You can see on the left-hand side it's 1983, on the right-hand side it's 2023, so you can see the ocean is warming. And the same for sea level changes. I will just cut it short a little bit. And this is high-resolution regional climatologists. I have a poster here in the corner, so we can talk about it in more details here, but they all on 3 different special grids. They all have 7 decades or 6 decades, and we already starting to renew. We have a couple of them in version 2, so it goes all the way up to 2022. Okay, so a little bit bragging. We have this plot which we like, which we love to show to the bosses. This is how often we are cited by you guys, by researchers. So it's about 3 citations every 2 days, which we are very good on. And this is how we celebrate the World Ocean Atlas 23 release. So we can see Sid Levitus. He's retired now, but he came and to share it with us. So that's it. Thank you. Any questions?
All clear.
I see no questions, but I would like to make a comment because... Oh, okay, I will make my comment afterwards.
Thank you, Justin Buck. With the changes in the platform types that you receive and the data types that you're receiving...
I cannot hear, sorry.
Oh, weird. Is that better? How's that?
Okay, try again.
Okay, that's all I've got. With the changes in data types going into World Ocean Database, are you seeing changes in data quality or data precision as part of that?
We are trying to keep all the quality flags we got from originators. And since we're doing our own quality control, we're adding our quality flags. So you can use either of it or you can ignore all of them. So it's up to you.
Thank you. So the particular thread that I'm going down is there's a reduction in shipboard CTDs. Typically you have a salinity precision of 0.01. With a transition to autonomous platforms, which typically have precision of, CTDs have precision of 0.001. The autonomy has precision of 0.01. So is that having an effect on the database?
Yeah, I'm very sorry, I have a problem understanding. Let's talk offline. Okay, sorry.
Okay, I would like to thank Alexei and all the team for all the impressive work that we are doing, which I would like to admit that it has inspired a lot of us for at the early stages of our careers. And just remind that Sidney Levitus, the leader of the Laboratory of Climate, was the first one who spoke about the global ocean warming. So for me, at least, it was a mentor for my work and for my next steps. So thank you again for this impressive work.
The ocean keep warming, so.
Yeah, sure. So you continue with all this work. So we can proceed now with the next presentation before the coffee break. It is from Clara Almejija from Spain, Centro Tecnológico del Mar, who will present us the stakeholders' engagement as a key instrument to devise the future strategy of your observatory.
Must I look for the presentation? Yeah. Almejija here. Okay. Yeah, it's too quick. Presentation. View here. Where is the presentation mode?
Slideshow.
Master art slideshow. Sorry. Hold it. Sorry.
You clicked on something.
No, this is. I'm going to close and open again. I think it's better. Here. And here, no?
From beginning.
Sorry. Good morning, everybody, and thank you for here. And thank you for attending my presentation about the stakeholders' engagement. I hope you find it interesting. Let's go. To begin with, I would like to give you some information to understand Galicia a little bit better. Galicia is in Europe, in the northwest of the Iberian Peninsula, that has 8,000 kilometers of coastline. Okay, the 20% of this coastline is in Galicia, which means that we are a society completely dependent on the sea. We are fishermen or fisherwomen. We are shellfish harvesters. We work in shipyards, canning industry, fish market. And furthermore, we love sailing, diving, or sunbathing on the beach if it is not raining. So not this year. So as you can guess, in this context, operational oceanography is completely necessary to provide valuable information for different uses, marine safety or climate change effects, for give you some examples. Therefore, 15 years ago, 3 public institutions dependent on the government of Galicia founded the Observatorio Costeiro da Xunta de Galicia. The first institution is Meteo Galicia, that is responsible of meteorological data and models. The second one is Intecmar, dedicated to marine environmental quality control. And the third one is CETMAR, that is where I work. Focuses here in marine monitoring and new technologies. This public observatory is part of Observatorio Raya, that is a leading case of cross-border cooperation in the Euro region of Galicia, north of Portugal, where 15 different institutions are working together in operational oceanography. And both observatories work in 3 main areas: observation, prediction, and added value products and services. And of course, our data are open and available in our website, but they are also shared in the main European data aggregators, like Copernicus, Emosnet, and CDataNet. And here you are a summary about our capabilities. Weekly CTD stations, automatic buoys, weather stations, high-frequency radar network regarding to observing systems, oceanographic wave and weather models, but also Lagrangian models, only on demand by policymakers or marine safety, and different products and services like general ocean and weather bulletins for everybody, or specific applications for specific end users, like barnacle harvesters or kite surfers, sorry. So let's have a look to this interaction with the stakeholders. During 2022, we met more than 30 different stakeholders and users or potential end users of our information. All these stakeholders develop their activity linked to the blue economy, fishing, tourism, port activities, marine safety, and we presented to them a large catalog of oceanographic information from Raya, where this is the cross-border observatory, where the information of Observatorio Costeiro da Xunta de Galicia was also included. This catalog gathers a lot of specific information like time, space and resolutions, variables, units, and how data can be accessed. In fact, during these meetings, we took a laptop with us to find and download data that these stakeholders were interested in. We have 2 main goals with this study, assessing the awareness, use, and usefulness of our information, and identifying new oceanographic information valuable for a future use. This slide shows what stakeholders know regarding to the observatory information, and we don't have good news. As you can see in blue, more than 50% of our observational information on the left and products and services on the right are completely unknown for the stakeholders, and less than 1/5 is used at least occasionally, as you can see in yellow and gray together. Thankfully, information is better for forecasting systems where almost 50% of the information is widely used for them. Weather stations, wave and weather models and bulletins is the most used information, and attending only to the information of this public observatory, we assessed that 2/3 of our capabilities are well known, and more than 1/3 is commonly used for our stakeholders and end users. Not only weather and wave stations and models, but also oceanographic buoys and weekly CTD stations. So this is a good improvement for us. Previous unused information was presented to our stakeholders, and they highlighted some of this information, like highly valuable for a future use. Radar currents, oceanographic buoys, oceanographic models, because remember that they are already using the weather and the wave models, and the radar viewers products, where you can find waves and upwelling index. And furthermore, these are the mandate that stakeholders have to replay their requirements, their necessities. More temperature and salinity data to detect local problems or biological events. Time series of harmful algal blooms that are very important in Galicia due to the mussel aquaculture. We are a huge product of mussels. Improved models of wind, waves, currents, and also turbidity. That is very important for divers, professional and hobbyists, and it's very difficult for them to predict, and also for us, it's impossible for the moment. And the most required petition is the unification of all this information in only one viewer, accessible, useful, and reliable. And if it is not too much to ask, this viewer must be accessible from a mobile phone, because sometimes this is the only device that our end users have access to. And just for finish, I would like to share with you what we have learned with this interaction. Stakeholders demanded information that already exists in the observatory, so we have here a huge problem. We must enhance efforts in spreading awareness of the capabilities that the observatory already has. So now we are changing some things in the viewer and in the applications, and in the near future, we will carry out training activities to encourage our stakeholders to take advantage of our information, improving their professional outcomes. We must also improve data accessibility, standardization, harmonization, or maybe these are not the correct words after 2 days of Congress, and to ensure the data usability, following the FAIR principles. And we concluded that this kind of, the stakeholders' necessities and requirements must be taken into account to design the roadmap of this kind of small observatories. And if we do, this will be the first step for their future engagement. And that's all. Remember that we are a small observatory in the Iberian Peninsula, and thank you for your attention, and I hope you find our study interesting and inspiring. Thank you.
Thank you very much, Clara. A lot of activities. Are there any questions for Clara? I don't see any. I have a question. It was not clear to me from what I've read. Do you get governmental public funding or from projects and other activities? Because it will be useful information for many of us how to maintain such activities.
Okay, we are 3 public institutions, and 2 of them have a public foundation, yes, because they are the meteorological institution and the quality control institution, so they have funding, but not us. We are a public foundation, and okay, we look for our own funding.
So that's not so easy, I suppose.
It's difficult. Okay. A lot of Interreg projects.
Yeah. So thank you very much, Clara. So this was the last presentation from this morning session before the coffee break. So we break now for half an hour, and we reconvene at 11 o'clock. We are ready to start again with our next presentation from Antonio Novellino. Okay, thank you. So, Antonio Novellino will present us the IMDIS near real-time river data and boundary condition services.
Thank you very much, Sissi. First of all, good morning. It's a very great pleasure to be here. I see that probably this time is one of the most attended IMDIS since I'm participating. So it's really a pleasure to be here and present something that is about some activities that we are doing for a while on integrating river data into the marine data services. I'm presenting on behalf of some other people, so I'm just representing a big group that is working on this. So first of all, of course, we are speaking about a new component, a new data that is very important for the marine, because of course we have rivers, and from rivers a lot of stuff is going into the ocean. We are integrating in IMDIS Physics. Some of you already know about that, but IMDIS Physics is one of the projects that is implementing the European Marine Observation and Data Network. And during time, we also had, we were asked to have a focus also on the coastal areas. So we started working also on some new data that could complement some other data that we are making available in the system. The general philosophy of IMDIS in general, in physics in particular, is to make in situ data fair. We are building on top of what is already existing, so on marine data infrastructures and program, and CDataNet is one of them, of course. Building and adopting and evolving some common standards, and we have already seen some flavors of this yesterday. And of course, we were also asked to implement and integrate both real-time data and delayed mode data. Because, of course, we are serving many, it was a good point, the presentation before the break, to show how many stakeholders we may reach out with a kind of system like IMDIS-1. IMDIS Physics is about different ocean physics parameters, and as I said, we were also asked to work on river runoff. We are integrating continuous data flow, and it's you can already see here that in river we progressed quite a lot, especially in the past 2-3 years. So at the moment we already have about 1,000 river stations that are providing operational data. Why river? Because, as we said, we have a strong influence of what is happening at the riverside into the ocean, especially if we catch the features very close to the river mouth. And so we have a sort of continuous activity, because we have that rivers are feeding oceans with sediments, pollutants, litter. So the information that we can catch from rivers are quite important also for many of the marine strategies directives in general that we need to report for. And on top of that, there is also a strong need of river inputs for improving the modeling of, the water properties and metocean forecast. For example, in this, we see the outcome of past year Eurogoose meetings, in which, again, river was one of the main topic that was addressed by all the people. So it is important. It is important because it's providing the land-ocean boundary condition for many of the ocean-related studies that we are doing. We tried in physics to start developing this concept of European river node. So the activity started with the idea to try identify main rivers, because if we speak about rivers, we cannot deal, or we are not interested in dealing with a situation like that. We have many stations along the river course. So we needed to start with some, let's say, a subset of this information. We started with the main rivers. We started with the most reliable stations, so the ones that we know that contacting the people and the expert, they can support us with all the metadata in order to identify the different properties that can be collected in that station. And then, of course, we were interested in having operational data, because the idea was to start with the operational data and then keep compiling also, more historical data. So of course, we were also interested in identifying the stations that were the closest to the river mouth. So sometimes it's really at the mouth, sometimes it depends on also the structure of the rivers. It could be a bit back in the land. And then, of course, starting with something that is easy to be integrated, so the river outflow, then little by little, the idea is also to keep expanding in the other feature, but I will go back on this later on in the presentation. So starting from that, and why, it's that important to have an operational river node. This is just a snapshot of what we can see from a river station that is providing data operationally. So this is the flooding that we had about 1 year ago. Oh, sorry, 3 years ago. 1 year ago. Yes, it's 1 year ago. So you see that if you have an extreme event, then you have this peak, this spike in the outflow. And when you get that spike, it means that something is happening. And these are the movie from the civil protection that is showing how, this kind of phenomena can affect the coast. And then, of course, everything that you see in that movie, in that video, then it goes also in the ocean. And so it's important to have operational data flow, because on top of that, then you can implement some warning system or some algorithms. This morning we spoke about artificial intelligence, so having good data, it's quite important to do that. So it is important to have a lot of this data. So in order to do that, we, as we said, we started implementing the general outflow of the data, and nowadays this information is already available in the in modern physics subset in the central viewer. So if you go to the IMDIS portal, and then you have one specific themes that is river, and then you can already see all the stations that are providing data operation. So if you click on the station, then you can see the time series of the outflow. And of course, you can also download this data directly from the system, and then you can get, different data formats. But what is in behind? What is under the hood? We organize the data flow in a way that we are exploiting some of the technologies that you know. We have already discussed about that. So we are organizing the data flow into AirDAP data collection. And we are organizing the data at 2 levels. So we have a collection of the data in which we have all the values that are qualified. And then we have a collection that is presenting, let's say, the asset, so the list of the stations that are providing the data. So this is an example of the 2 data sets that we have in AirDAP. So if you interact with the metadata one, you have the full description of the different station with some, the names of the station, the position, and some information about the time range that they're covering. And then as a unique entry point, as a unique ID, you can use the station name in order to access the data set. And then if you interact with the data collection of the data, then you have all the features that has been collected by that station. Then, of course, we suggest to use AirDAP because we can easily implement federation with these nodes. And so we only need to verify, it's always between brackets, but we need to control the metadata and the data features in order to include this into the main collection. So it will be easily popped up in the central system. But why, we are also doing this because, as we said, especially for river, we are also serving other communities and thinking about, again, an easy way to support people that are not experts or may have not the same knowledge of the data format tools that we are using in our community. By implementing the AirDAP node, it's also easy to directly harvest this information from, for example, a spreadsheet, a Google spreadsheet. So if you use this command, for example, import data, and you specify that is a CSV, AirDAP is exposing CSV or JSON data, then you can easily see this data into your spreadsheet, and then you can play with standard, spreadsheet tools, so you can implement time series and stuff like that, and then you can consume this data in, many other ways. But as I said, this is already available. Now what we are doing is we are pushing the consolidation of and adding some more feature to the outflow. So we are really interested in adding some key components, for example, salinity and temperature, because they can also support a better analysis or a better production of climatologies, as well as also model forecast feeding or initiating boundary conditions. So somehow is also important. This presentation is also a call to action to you guys, because of course we need some help in order to identify also the key people that are collecting this data in the different countries, because we need to be in contact. And this kind of the information, especially if we speak about salinity, temperature, but also water quality, we are also very interested in adding nutrients properties in that. It's important to start working together and find, helping these people, because they are coming more or less from a different community, to be more connected with us. So if any one of you also knows that there are some entry points that could be services or people that we may contact, there are a lot of people of us that are here. It's me, it's Cici, Dick, Alessandra. We can be sort of linking people in order to being able and expand this very amazing product that is already serving many, many communities. Thank you so much.
Thank you, Antonio, very much. Are there any questions?
Do you plan to mix this with weather conditions, for example, if you want to predicting what happens in the future? Because now you have Samso in a river, I guess.
Yeah.
But then you don't know what will happen next few days if you're not looking at the prediction of weather, for example. But that is something you're going to...
Well, actually, the scope of IMONET in general, and we are working, this European node is working for IMONET, is not to present prediction. So it's staying on the data collection. But this data, once you have them, this node operational, then you can use in model. So you can, you can implement downstream services at your side and consuming all the data that we are making available. This is in the scope of the action.
Other questions?
A technical question regarding the ERDAP federation that you have in place. I assume that you have a pretty amount of data there, like a few gigabytes or even a few terabytes of data. And have you experienced any quality degradation of the service when you are delivering this huge amount of data through an ERDAP?
Well, okay, concerning the river, is not that big, because in the end they are time series. Although we are speaking about 1,000 stations, the amount of data is not that big, I would say. ERDAP has some problems delivering big data sets that are something like over 2 gigabytes in one chunk. So in that case, some tricks may be useful in order, or maybe you can play with the call, the query that you're doing in order to chunk a bit of data. You can do that. Or you can subset geographically, for example, the data set that you're doing. But yes, there are some limits when you start asking for a big amount of data. Yeah.
But you are still using ERDAP, so you're just...
We are still, well, actually it depends, because it is working very well in organizing the data collection, because as you can see, it's easily to be integrated and exposed in a fair way. But for example, for improving the visualization, we are already using a component that tomorrow Peter is presenting, the beacon, because it's faster in presenting data towards a client. So I would say, this is my personal view. I encourage and suggest to use ERDAP as a data catalog, because it's very powerful in order to offer different data formats and supporting the standardization of the data formats. Then on top of that, you can implement many downstream services that can improve and service the specific need that you may have. So it could be, a piece of the puzzle that we need to take in mind.
Okay, thank you.
Okay, maybe also to mention that there is detailed documentation
Thank you,
and
thank you again.
guidelines. Antonio, maybe there is existing documentation and detailed guidelines for those who are
Yes.
interested to
Yes,
have a look
absolutely. I
and,
mean, about
get the
AirDAP,
first.
I mean, I didn't mention, but you have a Docker ready that can be downloaded by GitHub. So if you explore a bit the Monet GitHub, you find it. Together with Ingestion, we are developing some guidelines. We are updating the guidelines, actually, because there are some new considerations about the standards, the way we need to write also the information on top of the data collection that can help a further and more wider use of the different tools that we're doing. And then, of course, having all these kind of settings, then we can implement other services on top of that. And as I say, tomorrow we have a presentation on Beacon. I guess Peter will show also how we're doing. Thank you again. And of course, I'm in the corners.
Okay, thank you. The next speaker is Marina Lipitzer. Broad ranges for quality control of coastal data related to marine eutrophication, the Mediterranean Sea case study.
Thank you. Is it the presentation already open? No, I have to close it. Okay, this one? Yeah.
Double click, yeah, comes.
Presentation mode.
Slideshow.
Yes.
Yeah.
And it's there? Yes. Okay, good morning, everyone. My name is Marina Lipitzer. I am from the Italian National Institute of Oceanography and Applied Geophysics. And this work results from the collaboration with the colleagues from the Hellenic National Oceanography Center in Greece. And it's about improving system to quality control data related to marine eutrophication using the Mediterranean Sea as a case study. So in order to start with a common understanding, what is marine eutrophication? It is a process driven by the enrichment of water by nutrients, leading to water quality degradation. And it is one of the 11 descriptors of the environmental status, according to one of the main European legislations, which is the Marine Strategy Framework Directive. And it's also an ecological indicator assessment by regional sea conventions. So it's quite an important indicator of the sea state. The Mediterranean Sea is usually regarded as an oligotrophic basin, so low nutrients and chlorophyll. However, it is characterized by several well-documented eutrophic areas, such as in the northern parts, and which are especially related to coastal areas, close to continental inputs, land-sea interactions and human activities, and so on. And in eutrophic areas, nutrient concentrations can reach very high levels in comparison with open waters. So, needed to assess eutrophication at a basin scale, there is of course a need to use multiple data sets from heterogeneous sources and also collected over years. So data quality control, it's of course a fundamental steps in data management. And what is traditionally done is to do control on metadata and on data, which consists on, null missing values, range check in global, using global checks, but also regional. This is to verify if data lie within expected extremes encountered in the oceans in a particular region or period. But these ranges are now available for the open waters. So these regional ranges may not be suitable for coastal waters due to their high natural variability. I show here as an example some plots using all data, so data without any quality control being done. The map on the right, left, is just a surface distribution of nitrate, one of the nutrients in the North Adriatic. And the red line on the plot represents the regional range, which is currently used to validate data. So if we use this range, we will remove all the signal of eutrophication. So coastal eutrophication will be no longer visible. and this is not really what we want. So the purpose of this work was to evaluate ranges of biogeochemical parameters in coastal waters to help this evaluation of data quality in IMDIS chemistry. The approach was, first of all, what we need, what we defined as coastal waters. And we know that, according to our oceanographic knowledge, we know that river inputs extend far into the sea. So first we were thinking how to define the coastal waters. And in order to have a standard method for the whole basin, we decided to use official layers. So we based on the EA coastal waters, which are, however, available only for the EU states. This is why we have to do the analysis only for the EU states. And in order to support the MSFD, we did this analysis for each sub-basins. So we used the AAA files, the AAA shape files. We used IMDIS chemistry aggregated data sets, and we selected only coastal waters and also transitional and territorial waters. And we split this also in different depth layers in order to do the analysis, the statistical analysis of several subsets of data. So for each subbasins, for different water types, different depth ranges, selected parameters, selected statistics, and then we compare this with the existing upper ranges. So what we ended up with, this is, for example, just the nitrate, one of the nutrient concentration in the different subbasins, the 4 subbasins, in the coastal waters, the green on the top, in the 0.75 range and the 75 to 100, and in the open waters. We also calculated the 99th percentile of all data and also the maxima. And we compared this using all data and quality flagged. So we see that validated data and all data do not show remarkable differences except for the maxima, and maxima are visible only in 2 subbasins, in the Adriatic and the Western Med. And the highest concentrations are usually observed in this top layer, 0.75. So we did this because now we do the validation in a broader depth range, which is from 0 to 200. So now we do not take into consideration that the variability is mainly related to the top layer. So we compared the ranges with the concentrations in the open waters. So the red area, the pink area, is the range of concentration now used, and the blue and green are the concentration in all using the 99th percentiles of data. So we can say that the current ranges can be useful, are suitable for the validation of open waters. But what happens if we look at the coastal waters? The situation is quite different. So the pink area is the maximum range of concentrations now used, and you see that most of the data are quite above. So even the highest upper range will not fit a large part of the data in the upper layers, and ranges are too low even for the bottom layers in the Aegean Sea. So you see, this is why we lost all the eutrophication signal. We looked in the literature, and we used the MSFD reports provided by the member states to compare, to see if the data we find are really bad, they are really out of range, or they are really environmental signals. And the MSFD reports confirm that these high concentrations are typical of really coastal waters. So then we did this analysis also for other nutrients, and the results are similar. So there is really a clear need of revised regional ranges for coastal waters. And we did this for the Mediterranean now as an example. Taking into account that the data distribution is not normal, we propose to use non-parametric statistics. So we used the 99th percentile of data as a limit for the quality flag 1, and the maximum of all data encountered in these data sets as the quality flag 2, which means which is according to the CDataNet standards, is the limit between probably good and probably good data. And data above the maximum are considered as probably bad. We are still working on this. On this process, on these limits, but we think that these statistics are more representative than the standard deviation which has been used so far. So, considering the statistics of the major nutrients, we can say that the existing concentration ranges are adequate for the open waters, but for the coastal waters, higher upper ranges should be adopted. And this work also indicates the importance of introducing an additional upper layer, because the concentrations in the upper 0.75 are much larger and the variability is much larger than the underlying layers. And the comparison with published data supports the correctness of the ranges. And we also have to point out that in coastal waters close to human impact, even the maxima need to be carefully inspected to evaluate if they are realistic. So literature comparison and expert knowledge are really important. And we think that this methodology can be used also for other sea basins. However, we faced a set of shortcomings. For example, there is a need of shapefiles of official waters. So I really enjoyed the presentation given yesterday by our colleague from Blitz on marine regions. So we really need coastal waters for all countries. And we also need to easily filter coastal data to support data validation. And again, I also recap what was shortly said before by Antonio, that anyway, these coastal layers, these official layers are artificial because we know there is a continuum between inland, transitional, and coastal and open water. So even the continental inputs may extend far, far beyond the so-called coastal waters. So in the next step, we will do this analysis also on other water types and implement this into the standard validation process, which is carried out within IMDIS chemistry. But again, I would like to point out that expert knowledge is always required for coastal and transitional areas, and not only automatic QC is needed. However, with the new improvement in artificial intelligence, maybe this can help to further set rules to improve our quality control. So I thank you for your attention.
Maybe time for one question.
Hi, Marina. Thanks for your nice presentation. Do I understand it correctly that finally you apply the automatic quality control checks and then you do a visual check again, and in the final product we have a mixture of automatic checks and manual human checks? Is that true?
Okay, so there is an automatic check at the beginning, yes, on all the data sets which come to IMDIS chemistry. Then there is a large harvesting, and all data are aggregated into a single aggregations. And then there is visualization. No, there's an application of rain check also at regional scale. And this visualization was done later on, but it's not it's not the basis of the validation. I mean, it's only the automatic check.
Also to complement that, okay, there is the automatic control, but of course always, as you know, a manual, visual, human validation is needed in order to to give the final green light for the data to go to the next step, which is products preparation. Because automatic control is not sometimes, especially in coastal areas, sufficient to give you the correct results.
And also, I know there is a contact with the data originator. So before,
always a contact with the originators in case of change in the flags that we are provided by the originator. So there is a complete feedback quality loop to ensure that we do our best in any case to ensure that the highest quality of data is served to the users. So thank you, Marina. We can go now to the next presentation, which is for IMONET bathymetry and the high-resolution seabed mapping to increase the resolution of the product for the European seas by DIX Hub.
Coming? Yes. Yeah, almost there. But I'm now looking for the button. Now it's on top, eh? Yeah. Yes. You got him? Okay. Yeah, I would like to present another part of the IMONET family, which is IMONET bathymetry. And in fact, it's making a high-resolution digital terrain model for all the European seas. And I do this, let's say, on behalf also of my colleagues in the consortium, especially Thierry Smit. He is the coordinator, I'm the technical coordinator. But Thierry is right now in Canada also presenting the same presentation. But we could not be at two places at the same time in that way. Our overall aims is what we want to do and want to do in IMONET bathymetry is to bring together, let's say, all the bathymetric survey data and also composite DTMs. And I have to explain it a little bit to you, because composite DTMs is that we have several providers. They already use their surveys, let's say, to produce a DTM for their own area. And that's what we call a composite DTM. And that happens especially if you have, let's say, national hydrographic services. They do that. So what we do, we bring together the survey data, we bring together composite DTMs, and also in the last 10 years, let's say, we also bring together satellite-derived bathymetry, because we still have a lot of areas, especially coastal, coastal transition areas, where we do not have a lot of detailed surveys. And then we are using the Sentinel data to derive by a 10 by 10 grid, let's say, also the bathymetry. And that works in a lot of the European waters because they are transparent enough, and it can work up to, let's say, 15-meter depth. And also we use LiDAR data because there's some LiDAR, let's say, on the coastal zone, which then takes a... And what we want to do is let's say, to produce the best digital terrain model for Europe. And over time, we started with, let's say, a higher resolution, but over time we are now in 150 meter by 150 meter, using, let's say, all the available data sets. But in addition, we work together with JEPCO, let's say the global product, because we do a so-called infilling where we don't have survey data. So then we make use of the back, let's say, back side of the JEPCO. And that's more based on altimetry at that time. While in the other way around, let's say the IMONET DTM is being used by JEPCO, let's say, to improve the JEPCO for the European seas. And that's the way also in the Seabed 2030 we have a very nice synergy, I would say, on the global scale. And we learn from each other and we try to get a better result at both ends. And then, of course, we make this DTM available for a wide audience. And you know, bathymetry is a base layer for many people, for many applications at sea, also in economy-wise. And that means that we have a lot of interest, and therefore it's presented through the central portal nowadays, let's say by the map viewer, and you can also download tiles. But at the same time, there are a lot of OGC services which are widely used, I would say very widely used worldwide, for people to have in fact, a base layer in their applications. And they project then their other data on top of that. And that's very nice. And also during these sessions, you see a lot of times we see that product, which we call the global base layer, and that's being used by many of the applications. Another thing that we want to do in the project is that we develop so-called digital coastlines using all the available satellite information, and then mix it together, let's say, with a digital terrain, and also with a digital tidal model to be able to have the coastline at 3 different reference levels, like lowest astronomical tide, mean sea level, and mean high water. And then, of course, look at differences in time. Now what we do for this, there's a lot of cooperation with CDataNet, because the CDI service that we presented yesterday and also has been named a couple of times, we use that as the backend to describe all the survey data that we get together. And right now we have more than 65 data providers that over time of the project, since we started in 2008, have come forward. And they bring every time new survey data, which we describe then with the CDI. We also have a sextant catalog, and we use that to describe the final products, but we also use that to describe these composite DTMs, because those are in fact semi-products, and we describe them in the same, I would say the same common model, ISO 19115. And then we use a lot of controlled vocabularies, of course, which are of course the whole CDI and sextant, they are supported by these controlled vocabularies, and that makes it possible to make a very harmonized metadata. And it also makes it possible then for the products that we make to refer always to acknowledge, let's say, the data providers and the details of their data. And that's the important thing. So there's also always a track and trace between the product and the data. And that's quite nice. Let's go further. So we have this mechanism. Let's say you have these 2 sources, the survey data and the composite DTMs. And then together with the process, we have the DTM itself. This is an overview of the CDI service. So right now we have about 40,000 data sets in there. We have also about 300 composite DTMs. And this is all the time evolving, because we have the project goes on all the time. But we have every 2 years we do a new product release. And that's, let's say, the way to show the new element. Then we have here the flow. So you see on the top, you see the data input. Then we have, let's say, a common tool for the processing, and we use the Globe software. That's a software being maintained by Ifremer, and that over time also became an open software, so everybody can use that. But it's not static. We are all the time maintaining, because by using it, let's say, and we work with regional coordinators, so we have divided, let's say, Europe in different regions, and we have a coordinator per region, which has let's say, a network of providers. And then they get a new harvest of the latest data, and then they have to improve, let's say, the previous version, because that's how you work. And therefore we are also working on more and more visualization tools, and also having an online globe to be able to compare the previous version with the new version and look at the anomalies between them. And that makes it, because these files are too big, let's say, in the end to handle just on your PC. You need help by a larger computing. And then, let's say, in the end, then we publish together with the metadata, and that's now is going through the central portal. So these are some examples. So here we have the, let's say, the globe, and we have then the coverage of the European DTM in the central portal, and there are many layers there. Just like Antonio showed you, there are several layers with different aspects. We also are now doing the Caribbean, part of the Caribbean, and this is, in fact, based upon data that is, let's say, countries and regions which are related to European countries. So we have the Netherlands, we have France, we have the UK, others. Let's say they have data sets, and they also have a responsibility for mapping and bathymetry in those areas. And we use that, again, of course, together with JEPCO. Then we have here this layer menu. So you see the different, we have a couple of legends, different ways to show the bathymetry. Then we also have this source reference layer, and that's in fact, let's say, the track and trace. So here you see the mosaic, which is behind every grid cell. And in this way, you can also do selections, but also you can click on something, and then you get the metadata of that specific data set that was used to create the DTM in that grid cell. And that's widely appropriate, and I think also widely, let's say, appreciated by the data providers, because it means in practice that we get more and more data providers wanting to join the project because they want to be on that map, they want to be in that mosaic. And it is a little bit comparable to the World Ocean Database. I think they'll say the same mechanism, that people love the product, and they want to be associated with that product, and for that they want to release the data and make it part of that let's call it beautiful product. And that's, so here's some examples of the metadata. And then we have also the survey tracks, so they come from the CDI. So in this case, you can then find let's say, the base data, the survey data. And also we have a simple download service, so we have tiles, and those tiles, each tile is about 1 gigabyte. So you can easily, in 8 different formats, you can download the data sets and use them in your own system, your own GIS, or you make use of the machine services, the OGC. We have WMS, WFS, WCS, and we have WMTS tile server, and also there is a CSW for the product information. And this way, let's say, a lot of people do that. And we have on average, we have about 10,000 downloads, let's say every quarter. And it's for a wide range of users. And also in industry, it's very interesting if you go to, let's say you talk to Fugro or some big companies in the offshore domain. They all use this product as their back layer. And they use it in a quite interesting way, especially with Fugro. In the beginning, they said a little bit, hey, you're competing with us. They said, no, we are not competing. We're making a generic product, which is 115 meter by 115. So it's nice for, let's say, pre-engineering. But the moment that you really want to do a pipeline or whatever, you need higher resolution. And they use now this product to show you what we know, but also what we don't know, and what they can supply you. And that's their business model, and that works very nicely. And also they are now also helping us, let's say, with same as with CBAT 2030. Also the industry is coming more and more saying, how can we use our data also in this model? Because we want to be associate, but also we are big users, so why not improve the product with our data to make it better? And that's quite a learning curve. We also have some high resolution areas where we go to even sometimes 1 to 10 meter. And that's depends a little bit on the local data policy, let's say. So we see several areas where we have very high resolution, and about 300 now, and most of them, they are interesting areas, let's say, like seamounts, that could be ravines, that could be very interesting coastlines, and that's really making progress. But it's difficult to go to a higher resolution as an overall, because if you go to 50 meter by 50 meter, it means you need much more data that qualifies to that, so it must be high resolution data. And we have a lot of multi-beam, but also still single beam a lot. And another thing is, of course, that in several countries, let's say, there is a limit a little bit what they want to make public, simply for safety and security. And that's nowadays is a reality, of course, in our world, that you cannot share all the data, because otherwise it might be used in the wrong way. And that's also with bathymetry. Now, this is an example of high resolution. That's in the forecoast of the Netherlands, and in fact this was an area where they used a new dredging machine, and they want to tire it out, and they made a very nice, let's say, trenches there, and that's then the level of high resolution that you can get when you zoom in certain areas. We also have a world base layer, and that is a common product using JEPCO and the let's say the AONET DTM, and it has been made in the same resolution, so 115 meter by 115. But of course, parts of that are then interpolated, because you cannot go from 1,000 meter to 150 meter. You still have, but you can work with this. And this base layer is a very nice product that is also being used a lot worldwide. And there's also a land DTM, I call it a land model, and that's done by satellite composite. And these are together, and there's also widely used, let's say, only as a OGC service. So now finally is just one slide more, I think, is that we have an international collaboration also with IHO and JEPCO, I already mentioned, and there's also IHO is maintaining a website, in fact a reference website where you can see all the survey data worldwide. And this is also again done by the OGC services, so they simply pick up our OGC threads and they put them in, and if you click, you can find the CDI metadata of different datasets that you are interested in. And that is also all a collaboration with CBAT 2030, I already explained. And then conclusions, we are a leading project in Europe, especially for the bathymetry. We are well recognized. It means that all the national hydrographic services more or less are now members of our group. We also have a lot of, let's say, research institutes, and they are complementing each other, because the hydrographic offices, they have a certain task, let's say for the fairways and the maritime seaways, while the scientists are more interested in the phenomena, let's say, the outliers and the special bathymetry, and they feel come together. In the beginning, it was a little bit difficult, because we had different social groups, they had different ways of operating, but we managed to put them all under the same frame, I would say. And now we have a lot of innovation, also looking at AI and in-painting and super resolution, let's say some new technologies that become available. And you see that both groups are very triggered, in fact, to work together on the same subject. And that's something that also happened in this way. AONET bathymetry became a team effort. In the beginning it was more a project, but later it became a team effort, and now everybody trusts each other. You know, when you have a base of trust, you get much better results, and that's they call it co-creation, co-design, but that's how it works. We have many users. So like I said already before, we have 40,000 downloads on a year. And we have also millions of OTC hits. And finally, that's the way we go forward. And we hope to do this for a long time still to come, to be able to every 2 years churn out a new resolution and a new release. Thank you. Any questions?
Thank you for the interesting presentation. How do you handle the huge amount of bathymetry data that you receive? How do you receive it practically?
Mm-hmm.
I mean,
I
think it's terabytes we're talking about.
Yeah, it's a total. But what happens is that we have we have this metadata system. So we describe all the data in the system with specifics. Then we have the data itself, and the data itself can be ASRI, it can be XYZ, it can be several formats coming from the multi-beam and the single beam. And these data sets, they all, let's say, there's the software called Globe, which is a local software that is provided to all the regional coordinators, and they use that software to process those individual entries. And then they have, let's say, a common grid, already the AWONET grid and the AWONET specifics, because they link it also to the metadata. And then they, in fact, bring it together in this we call it then their regional DTM. So they make a compilation, like a jigsaw puzzle, and that's all done with Globe. But what happened was that, in fact, they had to chop it up in pieces, let's say chunks, to be able to handle it in a good performance. And for that reason, we are more and more developing, together with Ifremer especially, let's say they are leading this, to make an online Globe, which is then served out by the cloud, and then the regional coordinators, they can work on the cloud. And this way, let's say, they can overcome the limitations of the, let's say, the processing, and they can look at the regional DTM in one go instead of having to chop it up in pieces. And that's over time, let's say, this process every time it innovates, especially based upon the feedback of, in this case, the regional coordinators, but also the data providers, because we also put more tasks, more and more to the data providers, that they already do pre-processing for us, and not just give us a raw product, but that they already do, let's say, the same Globe activity locally, and then provide that further. And that's the way to, let's say, to optimize your project. In the beginning it was small operation, but of course it becomes bigger and bigger, and then you have to change your way of operating. And that's why we're also now looking in artificial intelligence, because we still have a lot of gaps, especially in coastal areas. And at the same time, there are footprints. You can say footprints, training model, you could say, how certain foregrounds or forecoasts are situated. And if you use those, you can do a lot of in-painting. So if you have, let's say, 100 meter, try to make it 10 meter and still have a reliable outcome. And those technologies are more and more, of course, getting, we have seen a couple of presentations, but this is coming. And if I stand here 10 years from now, it will be completely different, you know what I mean?
Thank you very much.
So if there are no other questions, we can go. Thank you, Dick, very much. We can go to the next one. Presentation.
Next talk is Joel Assopaudi. IMDIS Decision Support System, User-Driven Aggregations and Analysis of Forecasts and Observations.
Okay, good morning. Good morning. So I'm Joel Assopaudi. I'm from the University of Malta, and this presentation is to show you a decision support system that we implemented as part of the iWaveNet project. It was an Italia-Malta project, and we had partners. So there is me and my teammates from the University of Malta, and there were other partners from Sicily. So the aim was to collect all the data, to try to collect observations and model data together so that it can be used by stakeholders and have an easy way of how data, so one can visualize the data, one can also focus on areas of interest and download what's needed and combine it. So we had data from various sources, so we downloaded data from CMEMS, our own HF radar data, and other from various stations and from various models. And we also added bathymetry data from a ModNet and also some satellite-derived products that we did for the Maltese coastline. And we did all this with using open source technologies, so to try to avoid as much as possible any licensing issues and try to keep the system as lightweight as possible. So to visualize, we used OpenStreetMap. Specifically, we used the leaflet.js library. It's totally free. It uses OpenStreetMap, and you don't need to have any API keys to run it, so like Google Maps. And we were able, once through it, one can overlay both vector and scalar data sets. On the left-hand side there, one can see the catalog. The catalog, they are all everything as floating windows, and the color bars and everything, they are all user customizable. So user can change, can select date, times, depths, etc. And one can see the color bars. The color bars are also customizable, and also whether one wants to see vectors or different shapes of vectors, etc. Then we also had, one can also right-click and view depth profiles for any specific area. So this is for products which have different depth levels as well. Same thing we did with time series, and we also allowed authenticated users to download data CSV. Okay. Regarding visualization of charts, we use chart.js. As well, JavaScript library, it's very easy to implement, very easy to. The nice thing about it is that when you hover on it with the mouse, it will show you the exact position, etc. So for the stations, we have a number of stations across, we had access to data from a number of stations across both Malta and Sicily. Okay. To collect all this together, the stations were, so all the stations, they had their own proprietary formats, etc. So they were sending the data to our server, and then we were sending them to the hosting server using API calls, using over HTTPS, using RESTful interfaces, the same way that we have seen in the previous presentations yesterday. User authentication, to avoid having any authentications, any complex authentications, and for security we just use single sign-on. We use Google single sign-on. User accounts are managed from the backend, and a user can just click on register and sign in with Google. And once it is totally free, where any user can register and all data is available to use. Now, the nice thing about this system is that we tried as much as possible to make it totally so it can be handled, it can be totally managed by non-technical users. So everything, even the catalog, you don't need the software developer, you don't need to enter the code to add data sets, etc. So there is a backend interface, accessible as well via single sign-on, accessible obviously to single users, to specific users, where they can add different data categories at different stations, etc. All data is transferred via WMS. So regarding we set up an NCWMS server, okay, and data, so the important thing is that data is accessible as netcdf on and available through the NCWMS server. And from the backend interface, one just links, as we are seeing from the window on the left. So one just provides the WMS address, and then one shows what variables are there, etc. And everything sort of gets populated automatically. The idea is to try to avoid as much as possible any maintenance, and so the system will sort of run as much as possible on its own. As a parallel system, it's not yet fully incorporated in it. We also set AirDAP. So we had Antonio Novellino who was describing about the AirDAP system. It's very convenient because it is able to provide data formats in whatever things that you like. So you just need to provide netcdf and it imports from them. If I wish to do a simple comment about AirDAP, one thing, now this may be a personal observation, they are too dependent on Java. And when you have Java, you need to have the exact Java version, and even with NCWMS, the main problem we had was setting up the Java servers. So if we find some way of trying to move forward from Java, that would be really, really great, okay? As I said, everything is based on open source technology, so on simple technology. So this system is hosted on a simple Linux virtual private server. Okay, just FYI, so there is the WMS. That's where maybe it requires a bit more memory. It's a bit more memory intensive. But the system is hosted on a system that only has some 4 gigs of RAM. Okay, so it's on a virtual private server on the cloud. And the technology, so the backend scripts are via Python, and we use Flask and Unicorn, and we use Leaflet and chart.js for the mapping, solutions, etc. All data is transferred as JSON payloads over HTTPS, so it's using the same idea of RESTful API. So the way that we are seeing RESTful APIs is sort of the future, so it also avoids having to open any specific ports, etc., because you use everything over HTTPS, and all data handling is done using Python. We also, another value-added service we implemented was the climatology section, where we combine data from the CMEMS, so the CMEMS tree analysis for our area of interest, and we combine that with wind data from ERA 5. From the Copernicus climate, if I'm not mistaken. And apart from showing the different percentiles, one can choose the different percentiles for the average for the different date ranges of interest. One can also see the zonation based on seacraft. There is this EU regulation regarding seacraft safety for pleasure crafts for the different categories. Okay, and they show sort of what sort of adverse weather conditions based on wind force and significant wave height that they can find. And this was done for our transport authorities, where one can find for that particular reason. For example, this was, if I'm not mistaken, for category D, for example, which were the area which had sort of as a percentage of safety. Okay, the system is operational, it's every day, so it's just the issue of making sure that you have new netcdf on the system, okay, available on the WMS, so to try to keep it as lightweight as possible. Everything is dependent on WMS, so to try to keep everything lightweight. As future work, apart from adding other models and value-added services, we are looking into using time series forecasting, especially for station data. Nowadays, we have seen recently there has been the LegLlama model, which is used on probabilistic prediction as well, apart from other AI techniques such as LSTMs, etc. So we're looking to incorporate that as well to try to extend special station data, and perhaps as well using technologies such as we have seen DINCOF, etc., that we try to map observations into to map them. That's it. Thank you.
One or zero questions.
There's a question.
Aha.
I want to pick up on what you said with, can we move on from Java to Python? This is also my gut feeling in a way, but could you elaborate a bit more on that? Why is that that you want as
So,
well.
now this may be a bit more of a personal opinion, okay? So but the main issue I'm finding with Java is especially the, for example, we're looking into using threads. Threads, if I'm not mistaken, is stuck at Java 8. Java 1.8. If you try to work it with other versions of Java, it's a problem. So if you have a server where you wish to have, for example, we have AirDAP and NCWMS. One of them, for example, and they need especially Tomcat to run. So because they are web technologies, they need Tomcat to run. NCWMS, if I'm not mistaken, I had to have it on Tomcat 9 because it is not compatible to the latest version of Tomcats, and AirDAP is available on Tomcat 11 because it requires the older version. So there is, and if you are trying to do that on a single machine, if you'll have lots of Tomcat versions running, and then memory needs to be shared, etc., etc.
Thank you.
So,
Okay.
thank you very
Move
much,
on.
Joel.
Thank you.
So our next presentation is for the International Quality Control Ocean Database from Simona Simoncelli, INGV.
I don't see the cursor, you know. I don't see the cursor. Where is it?
This is yours?
No, it's the previous one. The last one.
Last. Oh, I missed it, I think.
So good morning, everybody. It's a pleasure for me to be here to present the IQUD and the IQUD team work. So the goal of IQUD is to maximize the quality, consistency, and completeness of the long-term global subsurface ocean temperature database. And this is done developing and implementing an internationally agreed framework. So you see how IQUD is organized. We are, our structure comprises 17 nation members and a group of 30, 50 people organized into specialized technical teams. We have Li Jincheng and Guy Castelao as co-chairs, and the steering team that is actually coordinating the activities and giving scientific guidance. We work in close collaboration between experts and users, and we do that with the support of other, let's say, organizations, Cleaver, SCORE, and we have support also from IOD. So here, the big challenge is to have a climate quality ocean database. You have here the picture of the data, temperature data that are contained in the World Ocean Database that we actually use to do our developments. And this is a data set made by millions of casts, and which correspond to billions of dollars in economical value. These data sets has been gathered with many different purposes, which were not climate monitoring. And it is made by different data from different instrumentation, and they suffer of bias, and so there is a lot of science to provide to the users a good data set for deriving actually very important indicators like the oceanic content, which is the main climate change indicator, since ocean is absorbing 90% of the heat of the Earth system. So you have on one side the estimate of oceanic content time series made by two different, let's say, quality control procedure, one from WD and the other one is done from the Chinese Academy of Science. And you can see how in the layer until 2,000 meters, 80% of the trend, there is a difference in the trend computed that is due to the quality control procedure. And on the other side, you have the effect of correcting XPT bias in the calculation of ocean heat content. So this is the motivation to keep going, and this is to support the idea that we heard before, that data are not static. We need to improve the quality in order to gain, let's say, more accurate results, scientific results. So I will give you an overview of the main task team results. We are working on uncertainties. You have a quantification workflow chart, the uncertainty depends on the observing system, the measurement method, the instrument, and the platform. As first approach, the first version of our code as the uncertainty specification that is a type B uncertainty that derives from the manufacturer. But we are now working on the representativeness error, which is something that is demanded by the model community. So it's a way to describe the uncertainty using a single measurement to represent the gridded average for a certain spatial and temporal resolution. So we are working to provide different products, gridded products, possibly at monthly resolution, and a different also spatial resolution, and to provide on the side also the code to compute it. Another task that is now working on duplicate checking. There is a work on review on Marine Frontiers about duplicate checking. So duplicates are contained in the databases, but also they are important if we want to integrate data coming from different databases, as we have seen before. So this algorithm has been developed, and it is based on the metadata. So it is a DNA, let's say, identification of each data according to the metadata, plus some statistics of the data themselves. So it was important that we have this automatic check, but also we need the manual intervention to decide which decision to apply. It was important, this work, to also identify different kind of duplicates, perfect, probable duplicates, and also to identify some errors in the metadata that are actually pointing out the duplicates that are not duplicates in some cases. So again, we have a repository where the code is delivered and can be used by others. Another important task is the automated quality control. There is a work published last year by Good et al. And this is very nice work and new, I think, for the community. 60 different tests has been coded in Python, and they are contained in a repository that you can use. And all these tests have been, let's say, assessed. So these tests, the efficacy of these tests have been assessed, and also the combination of them. Again, we have a code repository, but the point is, the most important point is the benchmarking metrics that has been used to do this kind of work, and also the benchmarking data sets that have been used to run these different set of tests. So the idea is new to provide, to apply different set of tests to the same data set and provide a different flagging scheme or different flags so a user can decide which flag to apply according to the application that they want to run. Another important application is the expert QC, so it is a machine learning approach to QC the data. There is a pilot web application where actually the experts are interacting with this machine learning. So doing actual manual QC, we train the machine to improve and learn how to do the QC. And this is, again, the code is available to everybody. You can sign up to contribute and collaborate in this case. Intelligent metadata is another important application because we know, for example, that more or less 50% of the XBT data don't contain the probe type and the manufacturing information, which is essential actually to compute the bias correction. So important when we want to use all the data coming from different sensors for our monitoring indicators and application. And so the team developed this machine learning tool to guess according to the time and according to the location in the world of the data that have been gathered to assign, the probe type to the XBTs. The approach now is an ensemble approach in order also to provide the uncertainty of this methodology in assigning these metadata. Challenges. We have one product that is available through the NOAA NCIA service and through the WD Select retrieval on the side, so IQUOD on the side of World Ocean Database. And we are running the new version of IQUOD with the new AutoQC. But we are facing challenges because it takes a long time to run. So 1 month, even when running each data set in parallel. The technical team are implementing cloud-based solution to optimize the computation and the production. And we need also to check that what has been, let's say, developed and tested in specific data set is valid for the entire global data set. And so verification is necessary before, let's say, the official release of the data, plus the duplicate checking and the correction of metadata errors is very time consuming. So there is a low capacity actually to have people doing this work, which is really, really hard. And so what is the solution? Is to realize the World Ocean Database Cloud, which would allow for any IQUOD member to execute changes on the WOD in a cross-community version of WOD that then can be the operational and official one. So here we are getting to the importance of fair data, and there is a new task team dedicated to that because you have seen that all the developments are available on GitHub. But we want to improve the fairness of data and tools. And this is also done in synergy with the European project, Blue Cloud 2026, that established a cyber platform providing access to a federated data sets, federated infrastructure and data, and also analytical service and computing facilities for open web science. So this is done especially in the workbenches, analytical workbenches. We have a poster with Alessandra Giorgetti. So here the picture is actually simplifying what is the concept behind the workbench. We want to integrate the data coming from different sources, among which also the WOD. And we want to integrate data and metadata, harmonizing them. We want to remove the duplicates and do additional QC in a virtual research environment to provide added values, EOVs, data sets, but also the operational workflow for the community to improve. So in conclusion, main achievement of IQUOD are continual improvement of QC processes, enhancing metadata and uncertainty information, duplicate detection, and global data assembly and data rescue, which is an important activity still to rescue data that are not shared yet. And this will allow us a more profound understanding of the changing climate. We have more than 30 papers published. We are also publishing ocean best practices in public repositories. We have a series of data products that can be used to train models, but also to test a new quality control procedure. And we have this pilot project with cloud-based supervised machine learning training by expert. So the outlook, we are implementing outreach activities in collaboration with the IOD Teaching Academy. We want to focus on salinity, not only temperature. We want to keep going with the dialogue with the stakeholders in view also of digital twins application. We want to consolidate the open science strategy, fully adopting FAIR principle, and strengthen the collaborative approach through cloud-based solution to face this big data challenge. And keep going with the synergy with Blue Cloud 2026. Thank you very much.
Thank you very much, Simona, for this valuable work. Are there any questions? I see none. Maybe I could ask, how can someone become member of the IQUAD?
Well, we do monthly meeting, and just I can invite you to a meeting.
Okay. Thank you very much.
We are a very open community, so a lot of people here is attending actually the meeting. Some are, depending also on the topic that we are presenting. And no, it's very open community, so you're welcome to participate.
Thank you. Thank you very much.
Thank you. We have the last speaker, Haitham Assi, integrating deep learning and multi-scale ecosystem connectivity of the marine habitat.
Hello, everybody. Exactly the last 10 minutes before lunch. It's perfect.
And you only have...
Yeah, and the reviewers say that it's too ambitious, what my work, so let's see.
You see it?
Easy, yeah. It's this one. Thank you for this opportunity. My name is Haitham Assi. I'm from the lab of remote sensing, Haifa University. I'm a PhD student. And this work, I collaborated with my professors, Anna Brook and Dor Angel. Okay, we here gathered together talking about the marine ecosystem and the importance of it. So just not to remember always that they are under threat from human activities like overfishing, pollution, and climate change. And what I believe that what's missing in this field is the linking between the fish and their habitats. Almost people talk about it only on 2 dimensions, not in 3 dimensions and so on. So this work focus on linking between the fish and their habitats by helping with the AI and machine learning and the 3D models to understand the complex marine ecosystem by analyzing large data sets and uncovering patterns for better conservation. And the 3D model offers precise mapping of underwater structures, correcting the limitation of the 2 dimensions models. The objectives, our objectives include evaluation the current state of marine biodiversity using AI and 3D modeling, advancing seascape characterization methods, developing predictive models for conservation, and optimizing monitoring and management of the marine ecosystems. This is our flow chart. So I'm going to talk about the data acquisitions. We have 5 data sources, divided 2 parts. The first one is about the bathymetry, the second one about the fish and the biodiversity, then pre-processing using machine learning and the main model and our results. The case, it's in this research area in the Haifa coast, up to 30 meters depth, and includes specific marine protected areas like Rosh Hanikra and Akhziv. Data acquisition. So we combine data from airborne LiDAR scans, underwater videos, archived multi-beam echo sounders, and high-resolution 3D modeling from photogrammetry. Start with the LiDAR bathymetry. We use LiDAR sensor mounted on aircraft to capture the high-resolution bathymetry data. This involves pre-processing and classifying point clouds to remove all the noises and these things, to create the digital elevation model, or you can call it DTM. We reach a resolution of 0.5 meters, 50 centimeters, and it's very high resolution. We believe that we can reach up to 12 meters, but after the first survey, we got to 30 meters. To validate our data LiDAR acquisition, so we dived and look if what we see in the DTMs, yeah, this is what we have in the seabed. We can see in this one, this point, this is the channel, and this is it in the still cameras. I took it by GoPro. Move to the multi-beam echo sounder bathymetry. It's archived from the 90s and have a very large coverage over the seas, especially in the Israeli coast. We can see the difference between the resolution. See, the green one is the LiDAR, the blue one is the multi-beam echo sounder. The resolution of the multi-beam is 5 meters per pixel. See the difference? 50 centimeters to 5 meters. We're losing a lot of data till now. The third data acquisition is the 3D models from photogrammetry. Photogrammetry validates the LiDAR data in areas where there are missing information, like caves or cracks or underneath rocks. So we support it with the 3D models from photogrammetry, which are processed into detailed 3D models, ensure accurate and complete marine habitats. Okay. Talking now about the bathymetry. So the pre-processing step is using super resolution GAN, if somebody familiar with it. It's a type of machine learning model using enhancing image resolution. So I take this model and work with it on maps. And I got these results. In the left side, we have the multi-beam and the LiDAR. They were the data set. And on the right side, the enhanced, this is the output of our model. We can see that we improved between this one and this one. We improved for the multi-beam and the enhanced almost 80–90%. And this is an amazing result. Moving to the part of the biodiversity and the fish data set. We use 360 degrees cameras to monitor marine biodiversity. These cameras provide comprehensive data collection, offering advantages over the traditional methods. Like before, they dived, take tablets, and count fish and write what they see. Now what I'm doing, I'm fix cameras, 360 degrees, and come back after 2 hours, take this camera, and do it all over the year and different seasons. We need to support this data set, so we took BioBlitz from the authorities. This archived over several years to validate our fishing data set, focusing in a group of fish that can tell us the status of the habitat itself. Like if it's healthy habitat or not, it's with high biodiversity or not. We're talking about a group of predators, only 5 species. Also, I can't cover all of the species. In this slide, we can see the sampling point of the cameras and the BioBlitz. Here, the sampling point on the DTMs from the LiDAR and the enhanced photogrammetry, bathymetry. Now moving the pre-processing of the biodiversity. First, we need to detect and classify the fish. So we used YOLO. It was version 7, and now we're using also version 9 to detect its deep learning algorithm. And this is the result of the training. The precision, we got 80%, and we are ongoing. We had to support our data set also from other sources of images, because what we got is not enough. Here we can see on the left side video. There are small fish. Almost we can't see it with our eyes. Our model can do it almost perfectly. Here's another one with a big fish. It's moving, that one? No? Okay, never mind. Okay, so now the main model. We combine multi-scale geomorphometric feature to analyze habitats at different scales, enhancing our understanding of habitat complexity and connectivity. This approach integrates physical elements, scale, large scale vertical relief, and small scale complexity to provide comprehensive view of maritime habitats. Like these are different type of features. Now, I repeat again, the main goal is to bridge between the structural connectivity, that means the bathymetry, and functional connectivity, it's the biodiversity and the fish. So our approach is like that. Using machine learning, classifier like XGBR or convolutional neural network, we try in both of them because we don't know how it should be working. So the input is structural connectivity and functional connectivity data to the classifier. When training the model for low, mid, and large scales, we trained in three times separately. In the low scale, mid scale, and high scale. Then we combine them into a multi-scale model. The process is ongoing, and we have primary results. This is one of them. It's a special map with habitat suitability scores, low, medium, high, and very high. In the middle, do you see my cursor? No. Yeah? Okay, so in the middle is the big area. It's sand, so less diversity. And when we see red lines, it's where it's more complex reefs. And it's saying that it's higher diversity. Going to the conclusion. In conclusion, our work includes enhancing seafloor mapping with super resolution GAN, improving the LiDAR and the multi-beam resolution. We use machine learning, 3D modeling for biodiversity assessment, analyzing species distribution for monitoring. We employ 360 degrees cameras and YOLO V9. Data validation is ensured through photogrammetry. We see calibration for fish data and test areas for further advance our research. And that's it. Thank you.
I can allow for one question. Uta, come and meet me. Faster.
It is almost not a question to Haitham. Thank you, Haitham. Very nice presentation. But to dig, if that is a possibility for eModNet to take this data in such high resolution that he has collected.
No, I think, let's say, it's a brilliant presentation. I like very much how you use all these new technologies and bring them together and integrate them. And it's because, like I say, multidisciplinary approaches are more and more needed, and you are trying to connect, let's say, different worlds.
This is remote sensing. This is what we do.
Yeah, it's very good, and that's why also with the bathymetry, of course, you have very local bathymetry, LiDAR, and the LiDAR, of course, can fit in AMONET bathymetry excellently, no problem. If you have some good metadata, but you will have, I'm
Yes,
pretty sure. And but also what you do with super resolution, like I presented also in AMONET bathymetry talk, I said also we are looking into super resolution because it's a way to get more out of the pictures, let's say the satellite images, but could also be, of course, LiDAR and others. And also the multi-beam can be improved and that you can go in painting, let's say. And,
yeah, like we took the multi-beam echo sounder coverage, that it covers much more area. The satellites can reach, I think, less depth or less precise. So, sorry. So we can, I think, to train a model, it's that easy. To have the data, this is the problem. It's cost money and.
Yeah, of course.
Yeah. Yeah, thank you. Yeah, thanks.
Thank you.
I see no other questions, so that's it. So thank you very much all presenters for their very interesting work and for presenting us their latest progress. It is indeed very promising, the new techniques and the AI with the deep learning, machine learning that is being used. So thank you again very much for everything. And I think this is the end of...
One word to say.
Yeah, please.
Lunch.
Okay, so we break now for 1.5 hours. The lunch is again, as yesterday, in the ground floor. So be back in 1.5 hours from now. Thank you again for your contributions.
Hello. Anyone likes to start again?
Right, you. What came after Meta? Was that C-Search? What came after Meta? Was it C-Search?
Meta and C-Search. After that, C-Data.
No, I was doing C-Search. Yeah, that's right.
So we realized that you were also for the first time having a noise. I remember that.
This young guy? Yeah, you do.
Alexandra and Dick, are you ready? Are you ready? Let's go.
Okie dokie. Okay, everybody in this place? Shh.
So we are ready to start with the new session on marine environmental infrastructures for ocean observation. With data management and access, it covers different themes for operational oceanography, metadata and data system, physical and biochemical, geophysical and geological, fisheries and biological. So we have different themes across infrastructure activities, marine pollution related metadata. So a lot of interesting things.
Yeah. Very challenging session. Yeah. Maybe I can introduce Alessandra Giorgetti right now, because this is my established colleague, I would say, for many, many years, decades, in fact. Alessandra, she is the head of the Italian NODC. She's also deputy director of OGS, in the section on oceanography. But we go back a long, long time. Let's say she started, in fact, one of the European data management project was MEDAR with Yves Vermeer in the lead. And at that time I was not in there, but I was in a competing something, you would say. And later we started C-Search. We came together. And from that point on, let's say we had the whole twist of the CDataNet, CDataNet 2, CData Cloud. Then we started with EMUDNet. And right now, Alessandra, she is the coordinator of EMUDNet chemistry. And she's also involved, let's say, in the EMUDNet ingestion. And I would say she is a very expert manager nowadays, starting from a scientist, becoming more and more a manager, having also a big group of very expert people under her. And she's a very good colleague. So I'm happy to work with her, and I hope to continue doing that for a long, long time.
Thank you, Dick. So now it's my turn to introduce you. I don't know if it's needed. You are well known, well positioned, but anyway, let me give you some information. Dick, he's a Master of Science in Coastal Engineering. He is Managing Director of MARIS and has a background in working as project engineer in Rijkswaterstaat North Sea Directorate, the Netherlands Public Works Department. Dick is coordinator of the EU-funded IMDIS data ingestion project, and he is acting as technical coordinator in many EU-funded projects like CData Cloud, the Blue Cloud, and all the series of CData Cloud 2, CDataNet 2, CData Cloud, Blue Cloud 2026, and the EMUDNet chemistry, EMUDNet bathymetry, involved in EMUDNet physics, and okay, I will stop here.
Stop there, please. I'm becoming shy otherwise. Okay, let's start with the program. And we had agreed that you would introduce the first speaker.
Yes, okay. The first speaker is Connor Delaney, and he will present the IMDIS Central Portal, how federated web services led to a centralization success stories. Connor.
Connor, you have the keynote, so you have 20 minutes and 5 minutes for discussion. So that's good?
24 minutes.
Look on the wall, okay?
Okay. Do I have to run it from here? Yeah. The presentation, yeah. Okay. Yes. Yep. And is it just by the keyboard? Okay. Hi, I'm Conor Delaney. I'm from the IMDIS Secretariat, and I'm a very proud member of the Central Portal technical team. A bunch of awesome people a lot of them are here today, and we're taking the opportunity to reveal at our show at this meeting some of the decisions that were made during the massive work of centralization of IMDIS, because we realized over the course of the centralization process, it might have been obscure to some people just why some decisions were made, and we thought that by giving these slides you could have a better understanding. And also wanted to show how the centralization of IMDIS was very much built on the groundwork or the foundations that the IMDIS community had done previously with the development of web services and metadata standards, which allowed us to build a centralized IMDIS. So, okay, next slide. So IMDIS vision goes way back to 2008. Just in case, for those of you who don't know, it's a long-term project from the European Commission aimed at gathering data, marine and ocean data, oceanographic data, and publishing it as data products for Europe. Prior to 2023, there existed 7 separate thematic portals. One data ingestion portal and 1 central portal. So that's 9 separate portals. And each of the portals looked different. You interacted with them differently. And they were all doing a great job. There's no criticism of the work they were doing. But as a user, you had to change how you interacted with portals as you went from one to the other. And the Commission really wanted this to change. They wanted to have a more consistent interface for users, because they realized that there was a risk of people not being able to access the amazing products that people in IMDIS are producing, and that the goal of IMDIS is the product that IMDIS produces. Just to give you an overall idea, IMDIS produces products from the seabed all the way up to the top of the water column, including human activities and natural activities from the environment, marine environment, and it's across many different thematics. And I was just discussing just beforehand with Mick Lully from the Marine Institute. We were just talking about metadata and one of the great challenges of metadata. And the thing about IMDIS is metadata is very much on our minds all the time. And one of the reasons for that is because we're across 7 different thematics. So you're talking about metadata from human activities, for example, and then metadata from physics or metadata from bathymetry. All are coming from different areas and are thinking about different ways about how data is represented. And there was general tenets for the IMDIS community from the very beginning, was that it would provide services to discover, visualize, and access open and free data and data products, use Inspire standards, use FAIR data principles, create aggregated and harmonized data products, searchable metadata, and it'd be multidisciplinary, as I mentioned. But now, if we go back to this first tenet, the services to discover, visualize, and access open and free data, that's not longer the case. The tenet now is that we are service to discover, visualize, and download open data from the central portal. And I'll come back to that shortly. So in 2020, DG Mare approached the IMDIS Central Portal team and the Secretariat and our colleagues in VLIS and said that the IMDIS Central Portal, which had existed as its own domain and its own website needs to be ported to the DG Mare, to the Europa domain, which is called repatriation. And this was a rule that came from DG Com. And DG Com had decided that projects websites such as eModNet needed to be brought on board to the European Commission domain. So we started that project, and that has lots of knock-ons, which I'll come to in a moment. And we moved eModNet central portal onto the Europa domain. So if you go there now, it's the one central portal is on the Europa domain. But that meant that we had to follow the European style guides, European Commission style guides, the corporate look, colors, the information architecture. And you see that when you go now, if you remember the old eModNet portals, they had a lot of orange in them. We have very little orange in them now because that's not one of the colors in the style guide. We have to follow web accessibility rules. And we have to follow rules on information architecture. For example, we're only allowed to have one map viewer, and we're only allowed to have one catalog. And we're only allowed to have a limited amount of menus on the menu bar. And these are all things that we have to take into consideration when working on the central portal. So when we started working at centralizing eModNet, the challenge was that we had to move the 7 separate portals into one portal that captured the essence of the products of eModNet and it made it easier for users to access the products of eModNet. We also had to get rid of had to create one central catalog, and we also had to get one map viewer. Now, for the map viewer, we were very lucky that Bathymetry decided to offer their code from their map viewer, and we took their code as a base, and we started working with that. And then we realized that we couldn't start from scratch with everything in eModNet because we just were too small a team. We had to rely on the web services functionality of all the other portals. And the idea being that they would continue to publish their data services, but at the end of the project, they would switch off their portals and map viewers. So that's what we did. And this is as technical as we get on this. I'm sorry for not being too technical, but the overview here is what exists in concept for eModNet. On the far, each eModNet lot has a geodatabase, or maybe it would have a thread server or an AirDAP server, or it has a catalog. We have a GeoNetwork catalog here, but it's not necessarily always a GeoNetwork catalog. The eModNet portal aggregates all these. In some cases, we copy the data from the thematic lot to a central server in the Flanders Marine Institute, and we do that for performance reasons. And then we use the central map viewer and the central catalog to give the impression that it is a centralized service. But really, it's still a federated system in the background where the thematic lots are publishing their services and data products through their data infrastructures. So for us, the geo servers need to produce web mapping services, web feature services, web coverage services, and also there's tile services there. Bathymetry produced those. And as long as they were all in OGC compliant, then we could use them. So with the GeoNetwork also publishes an OGC catalog, and we use that to accumulate or to aggregate the catalogs so that we produce one central catalog at on the eModNet website. We also brought in a new technology called AirDAP, and the reason we brought in that technology is to allow for the subsetting of gridded data, and that is a requirement that came in from the Commission, and I will show you in a moment on that. So it was important that the user has a common experience across thematics when they come to the eModNet portal. So here we have an example of the biology data, and biology publishes some of the data in web feature services, and the Commission were adamant that you needed to be able to draw a box on the map viewer and subset the data below that box. And that was reasonably straightforward with the biology because we were using it through web feature services, and that's a thing you can do with OGC web feature services. That was implemented, but you also have to do that with other thematics. So for bathymetry, we're not using web feature services. We're using the data, bathymetry DTMs are in NetCDF format. In that case, we unified the DTMs into one single DTM, which we put on an AirDAP server in order to provide the functionality to the user that when they draw a box, they can get the data within the box that's on the map viewer. And this has to go across all the layers. So all the layers that you open up, you have to be able to draw a box and get a subset across the data products across those layers. So the demands from the Commission, what they wanted users to be able to do was dictating what we needed to do in terms of what the tools we were using. And we had to use the tools that are available to our community. Just because we couldn't go and reinvent the wheel, we don't have the time or the energies to do that. So in the case of the AirDAP system, AirDAP is developed by NOAA, so it's very much based on ocean data sharing principles, so that was an easy reach for us. And I noticed there's a lot of people using it these days. I'm not going to talk about the positive, the negatives or the positives of it. It was just a tool that we were using. So with the GeoNetwork catalogs, it allows us to search through the metadata. It provides us one consistent approach. We populate the distributed tag field so that you are not just searching through metadata to get metadata, you're searching through metadata to get data. So you'll actually access the data through the catalog. And all the web services that we use are the same web services that are used by the eModNet map viewer. So when you come to use the eModNet and you do things with the map viewer and you download data, we're not using any special secret sauce in the background. We're using exactly the same web services that we publish on the website. So we are also, when we brought the catalog together, we realized that there was, even though people are using Inspired and ISO standards for the metadata, there was they weren't harmonized across the thematic lots. And that's a major job that we're doing now. There's no particular fault of anybody. It's just the way things were implemented. So we're working on that now to try and harmonize the structure of the metadata across the lots, because one of the things that has happened as a result of us centralizing is that we're now having more and more people using the eModNet, and they're expecting a consistent approach or a consistent API. So this is what I was just saying now. So if we go back here, this is where, for example, the GEOS portal are now harvesting the eModNet catalog, and because of that, on the GEOS portal, you can now display eModNet data products on their map viewer. And we didn't, all they did was harvest our catalog. In this case, we're looking at human activities data sets, and that was reasonably straightforward for them because it was geospatial data. But across the other thematics, you have to change slightly for some of them where you're going to get the data or how you're going to present the data, and we want to try and eliminate that so that if somebody writes code that gets data from eModNet, they don't have to change it to suit each of the thematics. And just on this metadata harmonization, I know I'm butchering what my colleague Tim has put in the notes, so if you really want to know more about it afterwards, take Tim outside and he'll give you more details. So as I said, we also present everything we do on this as web services on GitHub, and they're the same web services we use. So if you want to create your own eModNet portal, you can go ahead and use these web services, and you can do another one. So also we have the GEOS portal and the Ocean Info Hub. In this situation now for the GEOS portal, they're harvesting our catalog service for the web. With Ocean Info Hub, they're DCAT, Tim, is it? DCAT, I think they're doing? Schema.org. But in both situations, we were able to leverage tools that were in the current versions of GeoNetwork in order to meet the demands of these catalogs. But it was a great step for us, because one of the things that the Commission had been asking for years is that other services will be able to harvest the catalog of eModNet, and now they can. So we also had, because we're so focused on web services, we have to have a monitoring dashboard so that when anybody comes to us and says the services are down, we can find out if the services are down, or they can find out if we're having any problems. So I'm just going to finish this little tiny section. This section on this slide. This is an old slide that shows how the eModNet thematics work together to create data products, and it's a great testament to the success of eModNet that you could we work like this, and hopefully with the new changes to the eModNet portal, other people can use the new infrastructures to create similar type of products. But I wanted to move on to the human and resource realities of doing centralization. So we talked about the technologies we used in the background that helped us create the success that is the centralization. But the reality of the 3 years, or 3 years of centralization, is that we've had 147 meetings, the Central Portal team. I think that's over one of, I think it's 74 meetings a year, it was, something like that. And the Central Portal team is 5 of us plus a member of the European Commission. There's always a member of the European Commission on the Central Portal team. And the reason why the person from the European Commission is on the Central Portal team is to make sure that challenges that come from the Commission side, like challenges like we need to have follow GDPR rules, or colors on the website, or problems with logins, are handled in a way that we don't have to worry about it. So the meetings, the frequency of meetings is now reduced as we move out of centralization. We're centralizing data ingestion now. That's going well. It'll be ready this year. But that frequency of meetings has been replaced by a frequency of JIRA tickets, because we now had to, as part of all this, we had to create a tracking system for all our features development, any bug lists, and then we had to train up all our colleagues in the eModNet community to use JIRA, and they're now all JIRA masters. And the tickets get created on a regular basis, and it all has to be tracked and reported at the end of the year to the Commission on how progress is going along. So this is the transition from a data sharing network to an operational service of the Commission. And I would say now that eModNet is not really a data sharing network, it's a data publication service of the Commission, because it has to meet the regular rules of service level agreement rules of the Commission. So just on that as well, just on my final slide, and I apologize for maybe inaccuracies on this one, but I just did a quick back of the hand calculation of how many data servers are now operating in the eModNet network. So it looks like we have a centralized system, but we don't. We have at least 10 distinct servers across Europe, providing web services and data services and catalog services, which are harvested and brought together at the central eModNet server. And each one of these is I don't mean to, this is not a criticism, this is just a statement of fact. Each one of these is a potential point of weakness. The speed of the network is rated really by the performance of the slowest server in the network. You have a huge repetition of tasks across the network. So we have an Central Portal team tasks that we do, say, updating a geo network from one version to another, then has to be replicated across the network by all the other technical teams across the network. And the network is also dependent on the willingness of technical teams to carry out operational maintenance. We had a problem at Christmas where one of the servers in the network went down, and it couldn't be fixed for over a week because that institute that was providing that service was closed for that Christmas week. So these are the realities of moving from a data sharing network to an operational publishing system. And I will just leave it at that, because I was hoping that this will trigger some conversations afterwards, maybe tonight over some beers, because I think we need to start thinking about the future of how we're going to evolve eModNet. So thank you for this.
Thank you, Conor. So, Neil.
Thank you, Conor. 2 questions. Do you want the difficult one or the slightly less difficult one first?
So long as you don't ask me anything about ontologies.
No. So the first question, which is the less difficult one, just to give you a context. What's your relationship to the European data portal? Is there a plan to push all the metadata into the European data portal?
We do. Tim's the person to talk to about that. We have to get DCAT compliance, which we have. And so we had talked to the European Data Portal about them testing, doing a harvest, but I don't think they ever got back to us on that.
I mean, I'd be curious, because I asked for self-interest, because we've pushed metadata into there. We're not using the DCAT route, we're using the geo network route. and that's been really problematic for us.
Yeah.
And the whole way that they do their metadata quality scoring is also very difficult. So there's some interesting conversations to be had with the European Data Portal.
Just on that, thing what we're excited about is the Inspire, our group are launching a new GeoNetwork catalog, and we want to be able to go into that, being harvested like that, because that's going to make things a lot easier for us too.
Well, you'll see whether that's the case, because we did it from a newer GeoNetwork and it wasn't necessarily easy.
Okay.
The difficult question, sorry, Dick. So you mentioned the Commission wanted a common user
Yes.
It's back. So what does the Commission think the common user is?
That's a very interesting question. You can turn around another way and say the Commission funds these products being developed, and these products are owned by the Commission, therefore they're owned by the taxpayer, and they are all covered under Creative Commons by 4.0 open data license. So the Commission wasn't really concerned about who the user is in this situation. They wanted the user to be able to access and download the products. Now, there used to be a time where we took surveys of what users were doing, but that became problematic because it caused problems with GDPR compliance. And also it created a situation where we were having pop-ups occurring on the web page that was detracting from the experience of a user trying to get to data. So we may eventually go back to doing surveys again, and we actually have a permanent online survey on the portal, but the priority was to make it easier for people to access, whatever type of user it is, those data products. So, but it's a good question, it's a very good question.
Any more questions? Somebody with more questions? Neil, you have another one? No, it's Connor, thank you very much for a nice presentation, very interesting. Joanna, we are now continuing. We will continue now with IMDIS biology, and it will be presented by the coordinator, Joanna Bega from FLIS in Flanders.
Yes. Yeah, there you go. Good afternoon, everyone. So I'm going to skip this slide because Connor has introduced IMDNet, so I don't really need to spend too much time with it. And I'll focus on IMDNet Biology, which is a consortium with 24 partners. On the right-hand side, you can see a bit of a map of a network. In blue, it's our partners. In pink, the links to other IMDNet thematic lots. And then in this brownish color, the links of the partners with the regional C conventions, and on the black, it's other infrastructures or integrators. We do a number of things, like all of the IMDNet thematic lots, so we're not special in that sense. Publish data, create products, we provide services and tools for both users and providers. And one of the main remits is as well to support member states, EU institutions, and the regional C conventions. This is a very high-level overview of the data flow within IMDNet Biology. So we have data providers within our consortium, but also data providers which are external. They can be from EU-funded projects. They can be citizen science activities, NGOs, researchers in your institutes, for example. And the data that we publish is also shared with the OBIS, Ocean Biodiversity Information System, and GBIF, which is the Global Biodiversity Information Facility. And it will be found within the EU DTO in Edito Infra when it goes live later this year. So what do we do? So we do a data publication. So we have a remit from the Commission. We focus on 9 sub-themes, which
you can see from the images. And we deal with a lot of different types of data collection activities. It can be human observations, but also machine observations, imaging, tracking, acoustics, and we are now working towards integrating genetics. We do so by using and adhering to standards. So for the data on one side, and on the other side you have the standards we adhere to for the products. So we use a standard that is widely used within the biodiversity community, both by OBIS and GBIF as well, which is the Darwin Core. We use the OBIS-INF format, which allows for the link between the species occurrences or the taxa occurrences with environmental parameters or biotic measurements of the individuals. And we use vocabularies, controlled vocabularies. So we use worms for taxonomy, which has been spoken as well before in this conference. We use marine regions for locations, and the BODC NVS2 for any biotic or abiotic measurements, including sampling instruments and temperature, length, anything. And within the product side, because of centralization, we had to change our approach to how we publish our products. So we are now creating products in CF-NET-CDF format. It's not a straightforward job for biology as opposed to other disciplines, even though there is guidance, CF guidance on how the files need to be formatted. The inclusion of these files or the publication of these files in both GeoServer or ERDAP are not straightforward. So it's always a fight because the systems themselves, they don't really like them. They don't like taxa. So this is just a bit of a status overview of what we have at the moment. So we have more than 40 million occurrence records and 96 million extended measurements or facts. You can find them through the central portal GeoViewer and select the data that you want to then download. There are a number of filters which we will be expanding very soon. So at the moment, if you go to the viewer, you can only search by taxa, but we are in the process of adding other filters, so you can search by year, but also by data set, which could be quite relevant for you to show your management. We've submitted the data, there they are. And then in terms of the evolution, so the different colors represent the different phases. We are currently on phase 5, which ends in May 2025, so that's the darker blue. And you can see where we have the data gaps. So on one side it's a functional group, so we don't have a lot of data for angiosperms, mammals, or reptiles. And on the other side you have for marine regions. So Arctic, Mediterranean, and the Black Sea are the areas where we have the least amount of data. It's probably not very surprising for those of you working in marine biodiversity, and maybe within these regions, the constraints are quite well known. In terms of the data products themselves, so we currently have 38 products, but in the central portal viewer, we don't have them all on display. Some of them are quite old, so they remain in the catalog. As Connor said, they have CC BY licenses. We always aim as well to publish the procedures and the scripts required to create these products, and in a way that they are replicable, so you can use your own data sets and create a similar product with other data or for other regions. And then they are implemented in the portal with the adequate filters. Sometimes it's just taxa, sometimes we have time as well, so it very much depends. It's a varied approach. And on this one, I hope this works, because this is an animation. Yeah. It's not live. So this is the Calanus distribution that actually Charles developed in the previous phase. And you can see it's like model dated, gridded data, and you can see the abundance of Calanus through time. There is also an associated error layer. So this was done, I think, with the CPR data set as a base, right? Yeah. And this is just to showcase what we can do with the data that we have. I mean, as Charles said yesterday, even though we have 40 million occurrence records, we do have gaps in data. So we are limited in some areas on what we can do as well, and the type of output that we can create that is scientifically valid. So in terms of for external products, I just wanted to give a brief overview because I know that some of you might be working with other EU-funded projects that have a requirement to make your outputs available to IMODNet. So this is a very high-level overview of what we do. But if you have an output from a particular project that could be, we could host, republish. We do follow some procedures. We do an assessment of how relevant that could be for the biology users. And then we assess how we can best implement it in the GeoViewer. It's not always easy. So we're currently dealing with a product that it's a very interesting one, but the projection is not friendly with GeoServer. So we had to request to the providers if they could reproject the data so that we can actually use it. So it can take some time. As you can see, it's really not... And we have our procedures that we use for our own consortium on how to create NetCDF biodiversity NetCDF files, which is open on GitHub, so you can also have a check and come back to us if you have any questions. And then lastly, I think I have 2 more slides. Just a brief overview of other things that we have, like tools and services, and where you can find them. So I believe the slides will be online, so you can then follow the links as well. But we have a course on how, okay, I'm finishing. A course on how to reformat the data into Darwin Core, because that's the format that we accept, the standard. And we have a number of tools, both for providers and for users. I will be presenting the QC tool tomorrow, so I'll just leave it there for you now. Yeah, thank you.
Okay. Any questions for Joanna? Yeah.
Not you.
Thank you for the presentation. I have actually 2 questions. One is related to the data gaps that you were showing. So I was wondering if, for example, in the Mediterranean region, what we see is actually that data exists, but they are not shared yet. So this is,
yeah.
And so what you are doing to
we
disclose these data that are still.
Yeah, so we have some activities that, for example, in this phase, we had a workshop last year focused or targeting Mediterranean organizations, not just in Europe, but also on the southern side of the Mediterranean. But there were problems with visa applications, so a number of colleagues could not travel to the workshop. It was an in-presence only. It's also sometimes a political issue, so we can't overcome that in IMODNet. It's sometimes a cultural constraint as well, that data sharing culture is not the same across Europe, I think, as we all probably know. So it's targeted activities to going to conferences as well, presenting like Mediterranean-focused or Black Sea-focused. Yeah, it has to be like that, and trying to use the network for direct contacts, but it's not always successful.
Yeah, this was highlighted at the workshop at the beginning of the decade in the Mediterranean workshop, these gaps between northern countries and southern. The other questions is related to the submission of data products that you can. So is it a general, let's say, approach of IMODNet of embedding the products?
No.
Okay.
No.
And are you thinking of providing maybe requirements, so it is easier for who is producing the products to be compliant with your...
Yes, so that link to GitHub already has some of the requirements, at least for the files, but we will be having a workshop later this year for the EU-funded projects, mainly, to explain a little bit more about the data and the data products, for example, so that we can work together and make it as simple as possible for the outputs to be integrated as and when needed. It's really not an eModNet-wide approach, but we do understand in biology that we don't have the expertise across all of the sub-themes that we have to cater for. So, and it's better that we leave experts in a specific, example in mammals or in fish, to do the work that is scientifically relevant than for us to try and make up something that the community is not going to use because they will not trust it, for example. So, yeah.
Good. Anybody else? Question? Maybe I have one question. You said that you're also going into genomics. Can you say a little bit more about that? What your plans are?
We can say a lot.
Oh, just a little.
So, GBIF has, I believe, a year ago, 2 years ago maybe, published some guidance on how to publish genomics data. OBIS has followed on that as well, and we are trying to adapt those guidance as well for eModNet. It is within our remit for this phase to get a map with the distributions of the species or the taxa that are identified by genomics data. It's a lot of work because it requires technical development in the database, because genomics data doesn't work the same way as other types of data, as human observation data. The volume of data is also much bigger for genomics. So we're trying to integrate it, but it is complex.
What is the cooperation with EBI in that sense?
Well, yes. Well, EBI will have, as far as I know, the raw sequences. We're not going to store raw sequences. We're not storing that.
Could be a derived...
Yeah.
Okay, last question, because we have 5 minutes more, and then you.
Just a quick answer, because I'm with EBI, I'm with Magnify. We don't actually store raw sequences. It's mainly, we have a lot of different services, especially analysis pipelines. We can maybe kind of talk about this in more detail later. So I can just let you know what we can offer.
Good. Yeah. Cool, thank you. Okay.
Thank you. So we move on to the next presentation by Matteo Vinci on eModNet chemistry and the marine litter data management.
Yeah, we're on time. We're still ahead.
And how is going for the full screen?
Yeah, but the right side.
I don't see the full screen.
On the right side, you have 5, 6 buttons there, and one of them should be this one.
Sorry, but I don't see it.
Over the plus, you have the plus, and there is a symbol, I think.
Okay.
Yeah, you see full screen mode, the last one.
Thanks, Charles.
Yes.
Sorry. Okay, well, good afternoon. For who don't know me, I'm Matteo Vinci from OGS Trieste, Italy, and together with my colleagues from the Institute, the Consortium of eModNet Chemistry, and the international colleagues that are listed here, we would like to present you this Marine litter data management in EMONET chemistry, talking about how lessons learned in EU contribute to develop a global scale litter data management. Here, the outline of my presentation. We will see some general information about EMONET chemistry, and then we will go straight to the pillars and the lesson learned of our data management experience. We will start with a short recap of consolidated workflows, what format that were chosen were available from best practices. Then we will see quality controls, talking about pre-ingestion and post-ingestion activities. And for post-ingestion, we will talk about the aggregated collection generation and the data product generation. And as last, we will see the interactions and the outcomes with the EU and the global stakeholders. So EMONET is data management infrastructure at European level. There are several lots, as you heard, and between them we are the chemistry one. And we are dealing with the collection, standardization, quality check, and aggregation of marine data that can be relevant for the EU marine directives, but also for the global challenges. We are dealing with contaminants, eutrophication, and since 2016 with specific topic of marine litter. The network is pretty wide. The consortium is made of 45 scientific institutes and data management experts from 27 countries, and there are 5 international organizations participating. Let's shift our focus now to the marine litter data consolidated workflows, the aggregated formats, and their sources. In these years, we developed some workflows. So when we receive the litter data, we have a straight path for the metadata management that is going directly to the common data index system for the description and publishing of them. While then, for the specific topics of data that are the beach litter, the seafloor litter from trawling, and the microlitter data coming from floating litter and sediment litter, we have specific workflows. So for the beach litter data, we go through the agreed guidelines and format that were inspired by consolidated protocols and communities like the OSPAR, UNEP, UNEP Marlin, TGML, and then we go directly to our centralized database. For the seafloor litter trawling data, we go again through agreed guidelines and formats that were based on consolidated experiences and best practices like the IMDIS, MEDITS, and the fish gear. While for microlitter data, where the data management experience found was more heterogeneous and not so well consolidated, we created a new ASCII format that is the litter ODV1, and the data are going in the distributed infrastructure of the national oceanographic data centers. Let's skip now to the quality control workflow, talking about the pre and the post-ingestion phase. You can see here that in the upper left picture, we are talking about the quality workflow about beach and seafloor trawling litter, while in the picture on the bottom right side, we are talking about the micro litter from floating and sediment. Basically, for both the workflows, we have more or less the same phases that are consolidated now. So we are formatting the data through the agreed guidelines and format, using tools to make this work easier when they are available. Then we have a strong focus on the pre-ingestion validation phase, because this phase is streamlining a lot our activities and ensuring the quality of data. For this reason, we are continuously updating our validators, upgrading them due to our experience with the marine litter data gained in these years. When the data are validated, are considered okay, they are then ingested in our database or in the distributed network of the National Oceanographic Data Centers, and then we can have also some further additional quality controls in the post-ingestion phase, like for example, the aggregated collection generation and the product generation. Let's see the aggregated collection phase now as further post-ingestion quality control phase. For beach and seafloor litter, what we are doing is that we are using a new Python tool that was developed specifically for the data aggregation phase. So we are aggregating the data sets and revalidated them. And in this phase, it is possible to find quality gaps and updated needs. So we are correcting the errors, gaps, or anomalies found in agreement with the data originators. While for microlitter aggregated collection, we are using mainly the ODV software. Again, also here we are making correction of errors, anomalies, and we correct this in agreement with the data originators. There is also a strong work of harmonization in this phase that is done, for example, for the unit conversion, using the information that is described in the P06 vocabulary, or the merging of homogeneous parameters was possible following the description that is present in the P01 vocabulary, or sampling effort harmonization into two main categories that are the distance in kilometers and the volume of filtered water in liters. Of course, we are publishing the result of these aggregated datasets, and presently we are exploring more automatic ways to access and deliver these data products, for example, with AirDAP. We say that also the data product generation can be a relevant phase for the post-ingestion quality control because it can highlight errors and anomalies as in the previous phase, but it's also really important to be able to highlight relevant features of the phenomenon that we are analyzing. Because if the data are well managed, for example, according to the INSPIRE and FAIR principle, then it's possible to drill down and analyze them showing the features of the data. So for example, for beach litter, in the left side, we can be curious to show where the European beaches are surveyed for the macro litter, and we can find an easy, a simple way to show this. But we can be even more curious, for example, and we want to know how much are surveyed these beaches along the EU coast. And we can find a nice and simple and clear way to show this phenomenon. And we can further drill down, and maybe we will be curious to know where some kind of single-use plastics, like the plastic bag, are distributed along the EU coast. And the same is for seafloor trawling litter. We can show the trawling location on the seafloor, we can show where are located the fishing items like the ghost nets, or specific single-use plastics like the plastic bag in the seafloor bottom of EU. Now we are going to talk about the ammonet chemistry interaction within the expert groups and community, and I would like to start with the European part of these collaborations, starting with the strong collaboration that we have with the technical group on marine litter. In this collaboration, the consortium of ammonet chemistry is making the collection, the standardization, the analysis, quality control, and at the end, sharing through the national oceanographic data centers that are supporting the EU member states. So we can provide harmonized data set for the assessment of litter abundance, as for example, making baselines, trends, analysis of distribution. For baselines, for example, for beach litter, we have been able to publish already in 2019 a first EU marine beach litter baselines, while for seafloor and microlitter, there is an ongoing work about this. While for trend, since we already published the baselines for beach litter, there is an ongoing work to calculate the trends along the period about the litter in the beaches along EU. But in this collaboration, there is also space for new approaches. And for example, I'm talking about the International Expert Group for Seafloor Litter Images Data Management. About this topic, there is an ongoing data management proposal to upgrade and to implement, because the TGML goal here is to have an integrated monitoring approach that is merging together the seafloor images with the seafloor trawlings. Here I would like also to cite the relevant collaboration that we had in participation with the EuroQCharm project, that is a coordination and support action presently finished. This one was for analyzing, evaluating, harmonizing existing methodologies for plastic pollution assessment at European level. And the simple but really relevant outcome was that data management can provide a harmonized framework for data reporting, but cannot alone address the imbalance and heterogeneities due to not comparable monitoring methods. And for this reason, this is providing a great boost on quality assurance and quality control information management, improving this for better data comparability, more specifically for microlitter. And as last, here the collaborations and interaction with the global groups, starting with the UNEP Global Partnership on Plastic Pollution and Marine Litter. We are interacting mainly in community of practices for data and product sharing. Recently, they finalized and published their first microlitter a floating microplastic indicator that was built with a data set from IMODNET, so EU, MOEJI, that is Ministry of Environment, Japan, and NOAA from USA. In the right side, you have a preview of this indicator. Then we have the strong interaction with the Ministry of Environment, Japan, with their G20 microliter prototype group. We are asked to provide our expertise as marine litter manager. And recently, they also published their Atlas of Ocean Microplastic called AOMI. You have a preview of it on the right side, on the bottom of this slide. Between this collaboration, there is also IMDOS, not IMDIS, the crazy word of acronyms, sorry. It is another global community that is actively contributing and facilitating in all the previous activities. And I would like to conclude with this sentence that I like a lot in the last period. Is from P.J. O'Rourke saying that everyone wants to save the world, but no one wants to help mom to do the dishes. And I think that there is a great parallel in the global issue of the marine litter, and is a way from my side to thank all the people that are acting with their, let's say, small steps and maybe not so visible tasks that are contributing to tackle this global issue. Thanks for your attention.
Thank you, Matteo, for this inspiring presentation. Is there any question? Yes.
Yes, Bente Liljaby, Norway, not a member of EU. I noticed that you showed a map of the European coast. Now, EMODNET is a European service, but on the maps of some of your slides, we saw that it was probably the economic zone of Norway that was not included. Is that, obviously it's on purpose, but have you discussed? I mean, the litter is not really seeing the borders. So it could be useful even for the European Union to include it. Have you had a discussion about this?
I would reply saying that from our point of view, as EMODNET chemistry will be, of course, important, but we have to consider that we are interacting with the TGML official group that is considering, let's say, only the EU countries. So it will be really useful, at least for EMODNET chemistry, but we will have to see for EU TGML, which will be the case.
Yes, just to add, I mean, EMODNET chemistry has a data infrastructure, is covering also all European seas and not EU, not with no difference. But when we go to work for the Marine Strategy Framework Directive, in that sense, it is applied to EU member states. So, but this is a focused activity that we do together with the technical group on marine litter.
Any more questions? No. No more questions, Matteo. Thanks for a very nice presentation.
Thanks to all.
And now I have to announce, of course, the host of this meeting. And that's our big friend for a long, long time, Helge Zagen from IMR, and he's the head of the Norwegian Data Center. And he's going to tell you something about 10 years of National Marine Data Center, how it feels, how it works, what are the tricks of the book, everything.
What does not work?
How does it not work? I didn't want to say that, but everything that he has to reveal now. It's now your moment, Helge.
Yes. We have been a national research infrastructure since 2012, so it's actually more than 10 years. The first thing we start with is talking about data policies. Everybody that has data, they need a data policy. And IMR have had a data policy for a long time, but not all the institutions in Norway have had that. And if you have a data policy, you like to share data, you also need a to use a license. And we are promoting the Creative Commons CC BY as a license, which most of Europe does. And if I mention NMD and NMDC, it's two different things. NMD is my data center at IMR. The people of the data center is more or less in the room. I think there is 10 or 11 of them here today or during the conference. And NMDC is the national infrastructure, which has 16 institutions. We have achieved the Core Trust seal because we think you need to be certified as a trusted repository. We got the first one in 2017, and we have been reviewed once, so we have a second period now until 25. And we also got accredited as the Norwegian NODC from UNESCO, IOC, IODE in 2023. So we have kind of one accreditation and one certification. And everybody talks about fair. So what does it mean to us? We have a data catalog in the NMDC. It's not all data in Norway, but it's at least a couple of thousand data sets in Norway. And the data catalog means that you can find the data. Every data set has to be accessible, so that's the A. So that means on the red square that you can download the data that this metadata points at. And then the next letter, the interoperable letter, that's the really difficult part for us, at least for us. We are trying to use OpenDAP in some cases. We have both threads, hierarchs, and ODAP running. We haven't kind of decided which one to use, but we are kind of investigating which one is the best. This helps us on the eye. We're also told to put all our raw data available, and that's about 2 petabytes. And we're having an IBM system as our data storage, and then it's now about 300 terabytes a year increase. So you see that in 2015 something happened. You got the new research vessel, then 10 times more data doing nothing more, but you get at least more data. And we now get about, let's say, 1 petabyte in 5 years. So it has kind of stabilized around 250 to 300 terabytes a year. We don't know if it will be that in the future, but that's the current situation. And then to be able to do that, we make it available. We use object storage from IBM, which is an Amazon S3 implementation. So you make S3 buckets of the data. And you can use then CyberDuck as a client, more or less like an FTP client. Instead, it's an S3 client. You can actually then download 2 petabytes of data. It will take some time. I don't recommend it, but it's available. So it's back to 2010. So that's before 2010. That is, well, then we are looking at gigabytes and megabytes. And the last letter is the reusable or reproducible, whatever. And this table with the 16 data policies, that we started that work in, as I said, in 2010, 2012, and only a few of the partners knew what the data policy was. And early this year, in February, I got the last data policy out of the 15 partners. So it took 12 years to get all these 15 data policies. But they are all now green, and this is we are funded by the Research Council, so they have been kind of asking us every year, have you now gotten all the data policies? And I have to say no, but now I can say yes. And now we will send a new application, so then there will be new partners, so then I will be chasing some other institutions in Norway if they have a data policy. So there might be some red lines next year. And as I said, we're using Creative Commons, but we do have a same type of license in Norway, the Norwegian license for open governmental data. It's compatible with CC BY, so we use them both. And then this is kind of self-explanating figure. If you compare it to NetCDF format, that's also a self-explanating format. So I guess you just understand this. On the left side, there is the consortium of the 15 partners, the IMDIS, and then on the top, that's the kind of UNESCO and ISIS and World Data System, World Ocean Database, GBIF and FAO, which we share data with. And then on the left side, the European projects that we are involved in, both in CDataNet and IMONET and Copernicus, Olamur, Everyfish. There's a lot of projects. And the one at the bottom, that is kind of the coming infrastructures that we have been involved in that might be funded later this year. NMDC, we call it a distributed system. So we have 6 or 7 local nodes that we harvest metadata from into a central metadata database. And then we have the 10 partners that do not have their own local node. So then that is kind of the 7th node at my location. So I then have 10 partners in one node and IMR in one node and then the rest. And then we're also going to handle NIL real-time data. This is a sea bottom observatory in Lofoten, Vesterålen, Love, or Love, depends on how you like to pronounce it. You might have heard of this fiber cable that has been taken by a trawler. The fiber cable is not there anymore. A part of it it's there, but we deployed new equipment on the southern locations. But then early May, all power disappeared on the fiber cable, so no instruments are working. So we have to investigate, but no data is coming at the moment. And then we had a sailing ship from Bergen, a local boat. It's quite a big one. We equipped it with a lot of sensors, and then it sailed from Bergen in 21, and it sailed around the globe, used about 2 years. I joined it on Cuba, sailed to Bahamas, continued to Miami. It was a nice trip. We collected CTD cards, and the problem is that it takes about 1 hour to stop the ship. But then you can take a CTD cast. But we had all the data coming in every day, well, as long as we had the satellite communication, the data worked. There are some sectors in the Pacific and the Atlantic that has no connection, so then it takes a couple of weeks before the data flows. So all the data is on the NMDC portal, 10 cruises. And then, of course, we have worked with Copernicus. We are the Arctic data center for Copernicus. This is 1 month of data, some research vessels from IMR or University of Bergen or wherever. And then we add the rest of the data in the Arctic, so then you get the more coverage of the data. So we have a lot of data, but not too much. We work with NordDataNet, which is another scientific research infrastructure. We work with Emonet, C-Search. We worked with the ISIS data center, Neil. We do share data, and we share data with IODE and the World Ocean Database. So the 10 years have been a success, and we try to continue it with a new application. We call it the Norwegian Marine Data Space, because data spaces are the buzzword today. So we might know if we get a 10-year project later on this year. If not, we have to continue without funding. Then we have to rely on projects and so on. So, thank you.
Hi, Helge. Congratulations, first of all. But you were mentioning these licenses. In GEO, we are discussing not only interoperability between the different systems, but interoperability between the licenses as well. So I think you said that you were waiting for, the licenses to come in. Did you give directions to what license they should apply, or did you have to do, can I assume that the licenses are indeed interoperable, or how did you address that? Thank you.
We advised everybody to use CC BY, and we have more or less succeeded on the 16 partners that everybody does that. There are CC BY share alike on some pictures, but that is quite common. But then we have also approached some industry data, and because the seismic companies, they take CTD cast before they shoot seismic. And I tried to get some of those CTD casts, and I have offered them to Emonet, but the problem is that they say non-commercial, so CC BY NC. And then Emonet doesn't want those data. And if you kind of take CC BY data and CC BY NC data and put them together, everything becomes non-commercial. So you have to keep them separate, but if you use them, well, we do not do commercial stuff, so for us it's not a problem, but it is a problem when you have several licenses and you combine the data.
Thank you. Neil?
Yeah, thank you, Helge. It was very impressive. And who doesn't want to be part of the Love Ocean project? It sounds fantastic. I also have a question about the licensing. So what you were describing there, where you say you've got the two synonymous licenses, the Norwegian one and the CC BY. So how does that actually play out in practice? Does that mean that you have things that are with both licenses, or you have to choose one or the other?
I prefer to choose CC BY, but then some tell us to use the Norwegian license instead. But since they are compatible, it really doesn't matter. If you ask the Met Office, they kind of double license all the data with the NLOD license and the CC BY license. It's, well, it doesn't get more complicated, but I prefer just to use the CC BY.
Alexandra?
Yeah, maybe a suggestion on, like, the mappings are what saves the situation in these cases, but it needs these licenses to be published in controlled vocabularies that can then say that this license is equivalent to that CC BY license, and then you solve your problem and you point people to the mappings. Yeah. It's better to use one, yeah, but if you don't, this is a way to solve.
I think we have made them include in the text of the Norwegian license that it is compatible with CC BY.
It's not machine readable, though.
Okay.
No more questions for this gentleman who hosts us? He is responsible for tonight.
I can take any questions.
He's responsible for organization this evening, so. Give him a warm applause, okay?
So now let's continue with Hongming Lee and speaking about the Eurofleet Plus data management.
Okay, good afternoon, everyone. So today I will talk about the Eurofleet project data management that we set up to manage all the data collected during this project that were collected by a scientific crew that were on board of funded cruises by the project. So what is Eurofleet? Eurofleet Plus, it's a project funded by Horizon 2020. It has started in 2019 and then it did more than 4 years after because of the COVID crisis. So the project facilitated open, free of charge access to a unique fleet of research vessels from European and international partners, which has been arranged by 2 competitive transnational access calls. So a total of 28 cruises were funded, where scientists could go on board of these ships and collect the data to conduct their research. So for the second half of the project, these data have been collected and have been managed according to a common harmonized framework that applies fair and open research data principles. So for that, a dedicated work package task has been set up with the clear objective to optimize the management of scientific data generated during the cruises. It has been deployed as an integrated and uniform data management approach for all the 28 cruises, and it has been implemented in synergy with SeaDataNet network, a leading pan-European infrastructures for the marine data management, involving 3 NODCs as core partners, so Airbins, OGS, and HTMR. So together, we implemented a centralized and coordinated data management in collaboration with the scientists. So here you can see the complete data handling chain of the project. So I won't go into detail, but the data collecting during the cruises on board of the research vessels were gathered by the PIs and then deposited via IMDIS data ingestion portal to the assigned reference data centers, which would elaborate further the data to be published in SeaDataNet catalogs such as the CDI, SeaDataNet CDI service and the CSR service. And then they would be referred in the Evior portal developed during this Eurofleet Plus project. So in practice, how does it go? So when the PIs were funded for these crews, they agreed to follow a clear data management process that we defined, as you can see with a timeline here. So 2 weeks before the cruise, they needed to submit a full DMP where they would define the data types and the amount of data they would collect, but also if they would apply for an embargo period, and they would also define the data usage license they would apply on their data sets. The NODC would review and ask for updates of the DMP if it's not detailed enough. And then during the cruise, the data are collected. 2 weeks after the cruise summary report needs to be submitted to the SeaDataNet CSR catalog. And then 2 months after the cruise, or as soon as the data are available after the lab work, the data need to be deposited to their assigned data center or directly to IMDIS data ingestion portal for further elaboration and generation of CDIs. So here is the data flow for the common data without embargo. So as you see, the scientist, the PI can directly submit the data to EMODNet DIP. Then the data would be harmonized to be published on the CDI, CDataNet service. And for scientists who want some DOI to publish the data, we invited them to publish the dataset to CDataNet Sinoe to have this DOI. And this is also the data flow that we recommended for exotic data that could not feed CDataNet CDI service. To monitor the progress of the data management of the project, we define fairness indicators based on the repository on which the dataset would end up. So we achieved fair, findable, and accessible by publishing the data to EMODNet DIP and to Sinoe. And we could achieve fairness of the data when the data would reach CDataNet via the CDI service. So we did that for the 28 cruises in parallel until the end of the project. And at the end of the project, we ended up with all the DMPs completed except one. They were reviewed and updated when necessary. All the cruise summary reports were published on the CSR catalog and then linked to the Avior portal. And for the data, the scientists generated during all these cruises 164 data sets that covered a large variety of discipline purpose, as you can see on the pie charts, and also covering several sea and oceans regions as well. So over these 164 data sets, we managed to preserve 66% of them, so the PIs could send us these data. 10% of them were still under analysis in lab at the end of the project, and for the rest, the PI didn't reply to or remind us to send in their data. So we ended up with more than 20% of the data published on EMODNet data ingestion portal, more than 30 on the CDataNet CDI service, and 15% on CDataNet Sinoe, which corresponds to the number of applications on the plot below. For the fairness indicators that we defined to monitor the progress, at the end of the project, we reached 43% of findability and 27% of open accessible data, which will be increasing at the end of the embargo. And 30% of the data sets could be interoperable with 13 only reusable now, but at the end of the embargo, it will increase the rate to 30 as well. So in conclusions, there were many data sets generated with a diversity of data types that needed different expertise to handle it, but the NODC could, for 30% of them, make the data fair. And given the scale of the project, the amount of generated data and the time scale involved, we were very happy with this score because achieving 100% would actually not be possible with the time we had and the resources allocated to the data management of the project. So to achieve that, we had to well describe the guidelines, giving a lot of training to the scientists and support them for their data management plan, but also to communicate with them a lot to get the necessary metadata and data information to get the data more close to fairness. The biggest part of the work was to make the data curation process that enabled the data to be interoperable and reusable. So the main lessons learned from this experience is that the complete data handling chain is a long process which inevitably extended beyond the project, and that achieving fairness at a high rate is something which is quite difficult to achieve. That's why we are quite happy with the 30% of fairness. And also a key important thing that contribute to the success of this data management process is that a close cooperation was needed and was conducted by the NODCs to support the PI and to bring them more aware about the data management best practice and what is needed for the data to be fair. So I hope that these lessons learned will serve for other projects like current and future projects of the EU, but also for the project Aquarius, which is a follow-up project of Eurofleet, which also will give access to research infrastructure in Europe to marine and freshwater scientists for research infrastructure and cruise hours. So thank you for listening.
Thank you. Is there any question? You're perfectly in time.
Thank you very much for an interesting talk. Do you think if there was more funding available after the end of the project, your 66% would have been higher? And generally, would it have been a better outcome?
I think so, yes. So as we had only a limited amount of person months paid on the data management, we did the best we could. But the scientists commit themselves to provide data even beyond the project. So on a volunteer base, we can bring them to more fairness, but of course this is not the priority of our task now. But of course with more resources, I think we can reach a better percentage.
Yeah, I think it's very interesting, and it's a problem that we've encountered for years, that the data often arrive at the data centre after the project, and we've spent a lot of effort trying to persuade the funding bodies that they should give an extra 6 months or a year to the data centre to do the job properly, but they're not interested.
Yeah, I think they recognize more and more the need to have data management support for the data to be sustainably preserved. And since there was the COVID crisis, the project has been extended for the data management part already for 6 months, so we could extend our work, but obviously it was not enough to handle all the data generated.
Oh, it's good that it was extended for some time. Thank you.
Yeah, but I think there were also two things. We had the COVID, so it means that a lot of the cruises were going out deployed much later than originally planned. Because originally planned it was cruises and then do follow-up. But now the lead time, let's say, became smaller and smaller. And secondly, we had a lot of data which were samples, which have to go to laboratory processes, and they were not immediately available. So it was also, let's say, delayed time, because for the scientists even waiting for lab time to be able to process the samples. And that let's say, together gives you, let's say, you go over the end of the project. At the same time, of course, we hope that a couple of those scientists still will follow up later, that they come back and say, I want my data to be part of IMDIS and Copernicus. So here's my data, but that's on a goodwill basis, I would say. We have now in Aquarius, let's say, we are doing the same process, but there initially we planned it, let's say, that we really have the deployment of the activities, the TA, transnational access, and that we then really have a lead time to follow up. Of course, then later we want to use their own data, and together with the scientists also for virtual access and virtual research. And then the data must be available, because then they can combine their own data together with, let's say, other established data sets. And there if you look at the planning, let's say, if everything falls together as it should be, let's say, then we should be able to get a higher score. But there are no guarantees, you know. A scientist is a scientist, and a PI is a PI, so.
Yeah, but I think that the training of the scientists are really a key component to reach that. They need to be trained about data management practice and expectations.
Another question.
Yeah.
I have kind of the opposite problem of not having the data available, because I think that one of our ships has been one of the cruises that Eurofleet had, GeoSARS. And we publish the data on a daily basis. So we have sent the data to Copernicus every day, the CTD casts, and probably the thermoseismograph data. And we probably also published the data in our databases, and then you publish the data in Eurofleet, so there is at least 3 versions of the same data. So how should we solve that in Aquarius?
You're part of Aquarius, so we can discuss that.
Well.
Okay. Yeah, buy coffee. Okay, have some coffee. And now, before you go to coffee, it's very important, of course, that we have a poster session immediately after the coffee. And that's from 4 o'clock till 5 o'clock. So we want everybody, let's say, to have a very good coffee, etc., etc. But please come back at 4 o'clock, because we have a lot of posters, and people have done a lot of effort, let's say, to make those posters. And they would like to have your interest also for that. Yeah. And then after 5 o'clock, of course, we continue with the program. We have still presentations. And then tonight something awaits you, okay? That's the... Okay.
You're doing the first?
Yeah, okay. It's Steven. Yeah, okay. Yeah, I understand. But we have to... Hello, hello, everybody. Guys. I know everybody is excited, but please go to your seats. Everybody to the seats. Also the poster boys and girls. No, later.
And,
Okay. All poster persons, please go to your seat. Please. Meredith, go to your seat. Cook. Okay. Hi, hi. Yeah. Yeah, we can continue now. We have still a block to come. And we start with Stephen Piel from Ifremer, and he's going to explain about the new Eurogoose data policy. Go ahead, Stephen. Stephen.
So good afternoon. You hear me? No? So good afternoon, everyone. I'm standing in for Thierry Carval, who can be with us and send his apologies. So I'm also making this presentation on behalf of the Eurogoose Data MEC, which is the Data Management Exchange and Quality Working Group, of which Thierry is the chairman. And this work group, aims to help improving harmonization and integration of European marine data. So to introduce the subject, Eurogoose is composed of 44 members organization from 18 countries, and 137 organizations are involved as members from 30 countries. His vision is to sustain ocean observing and operational oceanography services, and his mission is to lead the development and implementation of sustained and coordinate operational oceanography across Europe. So to achieve this, it relies on the network of experts, several working groups, including one on specializing in data exchange, which is called Data MEC, and the teams dedicated to each type of instruments, and geographically for each of the 5 Eurogoose subregions, whose name you can see on the right here on the. Yesterday we had a presentation of one of the 5 sub-regions, the Arctic cruise. So concerning major data data policy initiative, no, I'm sorry. Yeah. So, yeah, this is the right slide. So, concerning major data policy initiatives, in 20 and 19, there were two key events. The first with the Open Data Directive Implementing Act on High-Value Datasets EU Directive, and the IOC Oceanographic Data Exchange Policy. So then in the 2021, there was the WMO new unified data policy with a core data which must be freely available and recommended data for which agreements can be needed. And all GOOS EOVs and ECVs are core data in this policy. And the second one with ICES, or with all data provided to ICs are considered to be public data under the Creative Commons Attribution License, CC BY. And then in the 2023, a revision of IOC data policy is underway, and the new Eurogos data policy as European implementation of the IOC data policy. It applies the FAIR principle, in fact. So to get to the heart of the matter, here are the main topics implemented with a core marine data shared with the minimum possible delay. Core, it means at least physical and biochemical essential ocean variables of the global ocean observing system. And also free circulation EOV data, of course FAIR, shared through open and free license CC BY, and available with minimal restriction on use unless there are valid reasons to restrict access, consistent with national jurisdictions, international conventions and treaties where applicable. And quality controlled and accompanied by metadata, accessible through a web interface and machine-to-machine protocols, and submitted to European and international open data systems, and engage Eurogos member organization and community to commit the implementation. So before reviewing the different parts of the data policy, I can already give you the key points, which are summarized here. So Eurogos data policy is the European implementation of IOC data policy. It is our commitment of ocean data circulation and use in support of European and global policies and societal challenges. And it promotes ethically open data, as open as possible and as close as necessary. Clear and unambiguous data license such as CC BY, long-term archives in the certified repository. This is very important to have data on the long term. And of course, FAIR principles, such as persistent and globally unique identifiers. So PED for better data citation and credits to providers. So Eurogos data policy consists in 10 concise and clear sections presented in the next slides. So don't worry, I'm not going to read the whole things, just what Thierry has highlighted in the bold here. With so section 1, data, metadata, and products should be accessible, reproducible, interoperable, freely and openly shared with minimum delay and restriction. Section 2, with this policy requires Eurogos members to share core marine data with the minimum possible delay. Section 3, the condition of use, so the Creative Commons Attribution License is strongly recommended here. Section 4, minimal restriction on use unless there are valid reasons to restrict access. Section 5, the free circulation of EOVs is a major importance for science and safety. So then section 6 with FAIR principles. Data should meet FAIR guiding principles, of course. And section 7, available data should be formatted and quality controlled with automatic QC and scientific QC also. Section 8 concern data repository, and Eurogoose members shall, where possible, use their national oceanographic data center organized by CDataNet or European International Observation Networks data systems. And section 9, sorry, it's to use to support long-term and secure archive with, for instance, WOD, OBIS, or WDS. And section 10 with detailed data and metadata sharing guidelines. So what we are now, Eurogoose data policy is now on Ocean Best Practice publication. You have the DOI here. So it is online. And what next in conclusion? The data policy is a commitment for the fair data with continuous efforts to improve citation and credits to data providers through DOI, best practice, and CDataNet vocabularies, and especially ENMO codes. And there is some synergies with Eurogoose RUSIs, working groups and task teams, with, for instance, Ocean Glider NetCDF format implementation, which is an international activity organized by OceanOps. There is also HF Radar NetCDF format improvements with global attribute and compression, which is a Copernicus and CDataNet joint data format. BGC Argo synthetic profiles toward Copernicus Marine Institute NetCDF. It's one of the formats for core Argo and BGC Argo data. And then CDataNet NetCDF and vocabularies for ship ADCP. With Eurogoo ship project funding, and cloud-native DAC, GDAC workflow also. So that's it for my presentation here, and you will find some useful links to find out more. Thank you.
Thank you, Steven. Yes, perfect.
Thank you very much. Congratulations with thorough work on your data policy. I couldn't help but notice that you have used several of the components from the GEO, Group on Earth Observations, data sharing policy. But there was one, you didn't list it as an inspirational source. I would recommend that you do that. But there was one difference, and in the data sharing principles, by the way, for those of you who don't know, every government that are members of GEO, they have confirmed that they will follow these principles. And GOOSE is also a participating organization of GEO. Now, what is said there is that we strengthen this statement that data should be open by default. This part was missing. Do you have any information on why you excluded that?
Unfortunately not. So I bring the question and for Thierry. Use the messenger. Yeah.
So, well, it's about licensing. Well, I'm a bit afraid you are creating a mess, especially in European countries. As you mentioned on your timeline, there was an event in 2019 that was the second edition of the Open Data Directive, and now it's a law in most of the member states, and so you will have in each member state the official open data license depending in Belgium of the government. That means that we might have several official licenses for open data. But basically, you would have on our website, these are open data under CC BY. And then we are also a Eurogoose member. You will have a long text that you say is similar, but is much more difficult to read, is not machine readable than just CC BY. So I'm afraid it creates confusion.
Everybody is confused.
Yeah, well, the task is not easy, indeed. Okay. Thank you. So the next speaker is Marcin, and he will tell us about unlocking the depths, IMDIS initiative, and Polish contributions to global oceanographic data.
Well, it works. It seems like it's working. Good afternoon, everybody. My name is Marcin Wichorowski. I am here to represent on behalf of a very broad consortium of institutions. What is the status of Polish oceanographic data and how we can contribute to global oceanographic data systems? This is a long history behind this presentation. Bit personal for me because I am not an oceanographer from the background. My career started with a computer science background, and working for Institute of Oceanology, I started at the beginning of millennium, connecting, networking with other people involved in development of marine information systems, especially IFREMER IMDIS conference 2005 in Brest. And when I was starting my communication with other people, I recognized that and I learned that Polish data, Polish oceanographic data is not so well visible, or we can also say it in much worse words, in world data oceanographic systems. I was wondering what is the problem, because over 50 years of operational oceanography in Poland and work of Polish scientists, oceanographers, must deep somewhere some oceanographic data sets which could be very precious, very valuable, but people are not heading to open this data to other systems. And my 20 years of work was tries how to open this data, how to dig the depth of resources, of archives of Polish oceanographic institutions and bring this data to surface. So finally, I could attract other organizations, my colleagues, to talk about how to publish these archives. And we start to develop project. The goals of the project were to develop and deploy a unified system providing access to data. It has to be, by definition, open access to data. So I approached two colleagues from key scientific oceanographic institutes in Poland, almost all of them, and we successfully submitted proposal to Polish governmental money and Digital Agenda Poland to develop such system. We have to make these data resources fair, just to make them useful for other users, especially oceanographers, which we are used to work together from all over the world. The goal was to extend availability of this oceanographic data both for Polish scientists, but also European organizations. and to develop advanced services for clients just to attract people and make them using this data. And more or less, this system is open for all stakeholders. So every scientist in Poland, every organization in Poland, but it's not limited to Poland, if has no resources to publish data, can get in contact with us and provide data sets. We will elaborate them and make them open. Consortium is quite broad. We have organized in 7 institutions, and as I mentioned already, these institutions is the top oceanographic institutions in Poland. Is almost 100% of oceanographic scientific data. Institute of Water Management is missing. Was invited to do this project together with us, to develop this project together with us, but they are competing with us in the same financing program, so we have to split, but we are cooperating close with Institute of Water Management as well. 4 of these institutions are former consortium of South-Baltic system. I have presented poster over there. So we have good tradition of working together, but we were in close contact also with colleagues with our institutions. And in fact, it was a bottom-up initiative. So we started to talk each other at the very low level, as the level of data managers, and we are trying to convince our managements and find solution how to develop such project. So it's very important that it's bottom up, because people are enthusiastic and are trying to dig into the archives and bring this data to the surface. Finally, we have completed work, and we have implemented in this system metadata standards. We have implemented vocabularies or organize our data to fit requirements which are defined by well-known data centers, global data centers. But we have to be sure that we are open for every oceanographic data. I was wondering how to do this, and it's much better and more feasible to attract people when they can provide data as these data are, and then our work is to elaborate this data and unify it within the system. Otherwise, people are not interested to cooperate. It is my experience from last 20 years that if I ask people to provide well-formed, high quality or quality checked data in a very well-defined format, they say, no, I have no resources, I have no time, so I am not willing to do this. When I ask people if they want to be famous and their data will be well known and provided by information system, they say, yes, okay, if I do not have to invest my effort, you can use my data and make it available. So this was the way which we were doing. Finally, this data is available in information system. The interface is very simplified for some reasons. First of all, we avoid to provide a lot of information in one place, but also this system is compatible with Web Content Accessibility Guidelines. So it has to be very simple, because otherwise it's not possible to fill the requirements of Web Content Accessibility Guidelines. This system provides a shopping bag, so you can select the information data sets which you are willing to collect, and you can take the bag at once after you complete your order. This system is well documented. It's an API documentation, so you can develop your own software and use and get access to data which is behind the system using API. This API looks like this. So you have access to catalog services for the web. You have access to open API documentation, JSON, and you can also generate API keys. When you are willing to search the system, at the first approach you can use free text search, but if you want to go deeper, you can just push search button and you will get access to over 7 million of data sets. I talked with Dick and colleagues from IMDIS many times, and they complain that this is a bit of junk. But it's much better to get access to very deep hidden data sets and then evaluate them. It's much better to do this such way than to miss something which could be very precious because we were not interested in doing the work and elaborate these data sets. So I'm pretty sure that even if 1% of this data could be interesting, it's still a large amount and a very nice set of information which could be very useful. So please check it. When you want to, okay, I have to be quick. When you want to go through this system, you can find searching criteria, bounding box, lot of keywords. I will go quickly through. You can get the particular data set and get access to data because it's a URL to real data. And you can get very different data format, which is also from one side a drawback, but from the other side, if you find something interesting, you have an API and you can use this data in your daily routine. So it looks like this. Also, we are providing Jupyter Lab to access this data. You can find a Python environment, Julia, also R and R Studio. You can also have develop Shiny applications, for instance, if you are keen on R. And then you can get access to real data, visualize it. Data is very variable. You can find, for instance, geological data also in this system. And what are the further steps approaching to the end? Further integration with CDataNet and IMDIS. Dick asks me every time when I produce CDIs. We have data open. There are systems with interfaces. I have to develop this software. It needs resources, and we will do so, but we have we need some time and some resources. And also, we want to get a certification because it gives us better recognition. So we are ready to do all these things and approach to recognition. And just for summary, there are 7 organizations, over 7 million data sets. Some of them could be very precious. Web content accessibility guidelines, interface machine to machine with API. So thank you.
Martin, thank you very much. I see there is already a question over there. And later I have a comment on your comment, okay? But
I don't know who I will put this thing, but I don't want to be an elephant in the room. But for 2 days now I heard about how easy to find data. And when I've been interviewing a few people, I mean, first of all, the data, stock market, influence, so many data you cannot get from the ocean because of the stock market. And then also a number of people don't want to give data because you can find bad things in the data. We get it when we interviewing people, so that's hard. And there's only a few examples in the military. So, I mean, it must be a lot of data that you can be hard to find, or is that just trivial to get all this data? Can you any comment on that?
I'm not sure if I understand properly your question, but
I mean, when we get one form of data, there are some people interested in to give data because they not really care so much because they can just give out the data. But there are many companies who make a lot of money on data. It's a living, learn millions. I mean, Norway is a good example. We have something called oil, and we have fish farms, and etc. Yep. We can just keep going for a long time.
But we are talking about scientific organizations.
Yes.
This data has been already paid by taxpayers.
Yes, I mean, of course, then
they have to be open.
We have that too, but that means we're also missing a lot of interesting data in some way. We get some interesting data, but just part of it.
Oh. I think it's another problem, because scientists have to do the job, to collect samples, to organize data, to create good data product, and it takes time, it takes resources. They also have to publish papers, because they are evaluated, how many papers they will produce. So very often they have no time to produce papers, because they are dealing with data. And I can understand these people which are collecting data, and they need to hold this data somewhere before publishing and opening this data, because they want to consume this data. But it couldn't last forever, so finally they have to open this data. It's a way to find a balance how to take this data from them. I think we are quite good with this in Poland now, because it's possible to unveil old archives and data which were not available till now.
Okay. Thank you, Marcin. I think you made a big progress in Poland. And by the way, you said that I said it was junk, but I never said this.
No. It was my understanding.
No. But I have asked you, let's say, can you aggregate a little bit, because 7 million is quite large, because you have more in Poland than the rest of all of Europe in our, let's say, in our definition. And that's why I asked you, can you, if you have a lot of time series, can you click them together, let's say, make a longer time series?
Yes. Exactly.
So it's a little bit like aggregation, because otherwise you have a lot of splinters, while if you deal with the whole package in one way, let's say you serve the users, and also you're more in balance with the others, let's say. And that was my remark, and that's still my request. And I've never said junk, because that's really completely out of the question that I say something like that. That's no way. No, I think you made very good progress, but I'm afraid that you have to get off the stage now, because we have to go on.
Thank you very much.
And tonight we drink something and we talk again, okay? Okay, we have the next presentation. It's by Linda Baldwijn. And she will tell us about shaping an ocean of possibilities for science-industry collaboration. So we're going now a little bit in the public-private partnerships, etc.
Exactly.
Okay, very good.
Yes, it's a slightly different direction to what we've seen, I think, the rest of the day. If I find the button to open this on full screen. I'm at the problem we were at yesterday already. Where's the full? No, can't find it yet. I can open it, yeah.
And then you go full screen, and then they take over. That's what they do.
How do I click on the full screen button? That's the thing.
Oh, no, you wait. But there is here a button for full screen somewhere.
Need some assistance?
Yeah. Yeah, the full screen is this one, eh? Oh, no.
Is this one?
Yeah, and then you say the last one.
Full screen mode, wonderful.
Okay, and now they take over now. Yes, we did.
Yeah, it worked. Should have sticked with a PowerPoint presentation, would have been easier than a PDF. Okay, welcome everyone. My name is Linda Baldewijn, and I'm very happy to introduce to you the SOUP Innovation Platform, shaping an ocean of possibilities for science and industry collaboration. And on the right-hand side, you can see all of my co-workers. And of course, I will be focusing on the data management part of this innovation platform. So what's the basis that SOUP started on? What are the challenges in today's ocean observation? Well, we can say we don't have enough ocean observing systems and information for society when we compare the oceans to the land. So there's like still a long way of improvements on information we could be gathering. And in addition, non-scientific actors are oftentimes completely ignored because why should some private person gather data for us? You know, it's too much effort and there's nothing out there that they could be using. Also, sensors are not properly interoperable. They are not standardized interfaces, and a lot of sensors stay in the development prototype phase or like don't even get to that phase at all. And all of the data handling is very costly and very complex and cannot be done by people who are just want to buy something out of the box. And that is something we want to change in SOUP. So our main dream is at some point anyone who has a little fishing boat or a bigger fleet of ships can go into a ship supply store and buy a little box that is there for ocean observation, and they can just attach it to the ship and get the data for us and for themselves as well. Because, I mean, people who go out onto the sea regularly, they're also very interested in knowing what is out there. And we want to use that curiosity for our oceans and partner up with industries to get these kind of boxes up and running, and also to increase awareness of our oceans. So that is basically the main goal of SOUP. And how do we want to do that? We want to open our research facilities because we know how to gather data from the ocean. We've been doing that for decades. And we want to include the industry partners and give them access to our research facilities and use those cross-sector synergies to improve ocean awareness. So, SOUP in a nutshell, it's building an innovation platform for more ocean observation and technologies. We started last year in March, and the project still goes until the end of 2025. Involved are 3 German Helmholtz institutions, GEOMA, the Alfred Wegener Institute, and Helmholtz Zentrum Herion, and we're being funded by the German Federal Ministry of Education and Research. That was the whole big project in a nutshell, but now let's come to data management, the thing why we're all here for and we're all interested in. So when we're talking about little boxes out in the ocean used by basically anyone, we're not talking about like maybe 10 ships that our research center is currently equipped with material, but we're talking about thousands, and then we need to improve the simplicity of our systems. For example, the sensor registration needs to be working out of the box. When you buy the system, you maybe have a QR code there, you scan it and your sensor is registered and the system already knows what it is, what it's measuring, and how to transfer the data. The only thing you might need to type in yourself if you're interested is the name of your vessel and who you are that is gathering the data. In addition, it needs to be scalable because currently technicians oftentimes need to go to maintain our systems, and we need to set up a workflow individual for each new system that is coming in, but that does not work on a commercial scale. So we need to set up our workflows really automatic so that it can be used on a larger scale. Also, when you suddenly open your system to thousands of new sources, security becomes a much bigger issue than it has been before. So making sure that the data transfer is secure and you do not get hackers into your research infrastructure is something that we need to pay attention to. And of course, we want to be able to share the data with everyone and ensure the interoperability. So we want to provide our data via the OGC Sensor Syncs API to everyone. As an overview graphic, you can see the 3 research centers involved in northern Germany at the right-hand side, and then out in the ocean, all the different stations and ships that are collecting data for us. And we are starting at the sensor registration. So our point is sensor metadata first. If we do not know what our systems are measuring, it's not really useful for us. So with the QR code ID I mentioned before, We will have templates in the sensor registration platform, and when someone scans their box, all of the information of what type of sensor, what type of calibration coefficients, and what parameters are being measured are automatically already filled in and registered. And we will know the system is being sold and should now become operational. We also need a platform on how to monitor all of the systems that are going on, and maybe even put in some system updates every once in a while. And for that, we'll be using a system called Beluga development at the GeoMAS. So here you could, for example, track where our little ship is going to and measuring data. Then I already mentioned the secure data transfer to make sure that all the information coming in is correct and exactly what we want it to be, and not someone else sending some kind of wrong data. And for that, I have more details prepared to you tomorrow in a poster where you can see how we can connect to the systems via VPN and transfer the data via MQTT or async to our systems and publish them through non-relational databases via the OGC SensorSyncs API back to the public. And that data can get ingested into our long-term storage facilities, backed up. And what we, of course, also want to do is use the data that is coming in for scientific purposes, so we need to apply quality control factors. Very interesting for non-scientific actors, the people who bought our little boxes, is actually seeing the data. So they want immediate access to everything that is going on for visualization, and so we will be using our API to develop some nice little dashboards so they can see what they are being measuring. And in the end, of course, we want to use the scientific data for the wider community and feed it into national and international research data initiatives and data portals, like we've seen a lot of them in the last 2 days. So that's SOUP and its data management in a nutshell. If you want to learn more about the innovation platform, please have a look at soup-platform.earth, and thank you very much for your attention.
Any questions for Linda? Questions? Yes. Maybe I have a question. Otherwise, Alexandra goes first, of course.
Thank you.
Ladies first.
Thank you for the very nice presentation. My question is, what do you use on the sensor registry? So you have a sensor registry.
Yes.
And you create persistent identifiers for your sensors?
We create handles for all of the sensors.
So
the persistent identifiers in form of handles. Yeah.
And you use the SensorThings API?
We use the SensorSyncs API for the publication of the data, and of course we will include all of the handles to the metadata.
And what about the description of your sensor?
The description is in the sensor registry, and it's described in SensorML.
Okay, so you use SensorML, and then the SensorThings API for your data.
Yes, and then you interlink both of them in the API, so you can go from one to the other and have all of the metadata available.
Okay, so I guess you will be looking forward to SensorML 3.
Definitely.
Because that's XML and it's, we want to, yeah. Okay, thank you.
More questions in the room? No? Now I want to ask you, because you talked about the box, and then in your example you showed the ferry box. But is that one of the boxes, the types, or are you focused around that ferry box?
Ferry box is a bit big to put on a little ship. So like there are different kind of ideas on how to do that, especially like because we want to measure in the water, and like telling people to drill a hole into the hull of their sailing boat is something that is complicated. So we're also thinking about maybe attaching like some kind of drifters next to the boat to have access to the water, but that's something like our technicians are currently in active development. So
yeah, but that's what you mean, that you work together with industry, let's say, to develop a whole range of boxes, let's say. That's called It's a Box, because that's an easy package that you can give to somebody at different scales, let's say. Okay. No, very interesting, because like I say, in your example you showed ferry box, and of course that principle was already
that is quite old and it's been ongoing, yes. But that's the basis we're coming from. We know how ferry boxes work. We know it works in principle, and now we just want to make it smaller and on a much larger scale for a lot more people to use.
And they also think about citizen science, in fact, in this way.
Of course,
Not only industry, let's say, helping.
The industry shall help us with building it, because we're not going to produce 10,000s of sensors ourselves. We need some industry partner to do it for us. And then the citizens, of course, are the ones that are going to gather the data, hopefully.
No, thank you very much. Very nice.
Thank you.
And then you take over?
Okay. Yes,
Dear
for the
colleague,
next
you take over?
speaker, Antonio Novellino, that will talk us about a first roadmap for data management solutions of low-cost ocean observing technologies. Yes.
Yeah, we're going there. We're going there.
continue.
Low-cost technologies. In fact, what Linda was also saying. So, yeah. Challenging industry.
Okay, good. So, good afternoon this time. So we are going, I mean, we started discussing about the potential of the citizens and the citizen science activities to contribute to the data monitoring. And I mean, this presentation is trying to give you a flavor of what we have already started thinking about and some streams that are already happening. But I take it from far away. So why we need data? I mean, we are living in, on a planet in which most of the planet is water. And we have most of the people that are living very close by the water. And we need, I mean, we are supplied by oceans for many kind of things. We are getting food, energy, materials. We do most of the transportation. We live for tourism. So ocean is global issues, and so we have to observe it globally. We have discussed it quite a lot. And we have also a common challenge, and so we have many programs and initiatives that are looking at monitoring, and we discussed about how to simplify and streamline the data management on this. This is also nice because if we look at some reports from OceanOps or in situ goes, we see that we have many platforms. We also have some information about, how much is spent at European level in order to collect the data. But although we can see many points in the map, if we really look at, the coastal areas, or if we look at, Southern Ocean or polar areas, or if we look deep in the sea, we are missing a lot of data. So we need to act on this, and so we need to find alternative routes in order to collect the data. And one way to do that is involving citizens. So involving citizen initiative and involving low-cost technologies in order to enable citizens to contribute to the data collection. This is also nice to think about that European Commission is planning, is requiring somehow to get 20% of the marine data to come from citizen science activities by 2025. So it's very close. And so, we have also to speed up in order to provide these people with tools in order to facilitate their activity and contribution to the different data collection. But, this is a survey that we did during another event. And we asked the people, what is the first things that comes to your mind when we speak about citizen science? And you can see here this word cloud, and we see that we have NGO, that somehow is one terms that is popping up, but is also engaging the public, awareness, more data, engagement, and so on. But if we go to the, let's say, the definition of citizen science is participatory science is scientific work that is done by ordinary people, so with no special qualification in order to collect the data. And somehow this has emerged as a very powerful tool and popular activity to engage and collect data. As we already said, also the European Commission is betting on this contribution. And we can also report that it is a growing interest. These are some of leaflets of events that have been done, and they are ongoing from past years. You can see the picture of Patrick that he was supposed to do this presentation that is also doing many of these initiatives. But if we look at some example, which are, example of citizen science, we have, for example, and the other thing is also that this kind of initiative are really getting a lot of awareness at the international level, because, for example, in this case, we have that science is also mentioning this activity that is a network of very cheap sensors that are used for ecological studies. So you plug this sensor all over the places. You can see in the map how many sensors have been plugged. And then you go there with a mobile application and you can scan and retrieve the time series of the temperature recordings. And by the way, also the accuracy of the sensor is quite high because it's 0.1 degrees. So for ecological studies, good enough for doing studies. And that's why it also took the attention of science. Or there are other guys or startups that are inventing or building up very funny tools that are very cost effective. So for example, in this case, these guys, again, got the attention of some British newspapers because they were building a small autonomous vehicle that can collect and can be deployed as an autonomous system, but is much cheaper than other competitors, competing solutions. But also, if we think about the contribution that other people that are doing sports, for example, scuba divers, can provide to the data collection is quite impressive. But we also have some examples that are already feeding IMONET. We have two, I would mention two main examples. One is the Ocean Data Networks, that is the network of fishermen that are using some smart sensors attached to their fishing net. And what is very interesting is that they are very complementary to the other data that we are already collecting. In the picture, we can see the complementarity of Argo profiles and this fishing-based collection data. The soup is another example. And the other one is in New Zealand. So we can see that we can also cover some area that at the moment in our previous map for IMONET are not covering. But another good example of citizen science project is also the Ocean Race. While they were racing, so while they were performing a race, they were also collecting data, and we were able to connect both the operational data, so the lines that you can see are temperature data that were streamlined operationally, but they were also doing some bottle sampling that they submitted to the British and German National Geographic data center, so we received it as a delayed mode. But we have a big potential, because if we think about all the kind of outdoor activities, water outdoor activities that we can have in any coastal areas, we may have a very huge potential on that. But of course, we have also some concerns, and again, playing with the some surveys, I would say the highest concern that we have is the perception of the quality of the data. So we need to work on that. And that is very linked also to the second point, that is data verification methods. So again, we are speaking about the quality and the way the people are collecting the data. So what we need to do is really to try and clarify the way and the methodology by which we can ingest and use this data. But we also have some legal concern, because as soon as we start speaking about citizens, we are also dealing with privacy. So there are ethics concerns around, there are some location concerns around, and so it's quite important to have clear also this distinction, because if you're speaking about let's say, a citizen science action in which you have a project, in which you have a PI that is involving other people, in the end you have this person that is the accountable person for the data. If it is a more participatory action, then again, it's a different way to manage this legal consent. So there are some issues, some things that we always have to think about when we start dealing with the new data streams. But, of course, we have to bet on this, because as we discussed, we have a very good potential on that. And some key messages, so I mean, steps that we can do is that we also have to think about the accessibility of the technologies. Because, for example, we have many citizen science actions that are related to census or abundance mapping, while we need to start using more the citizen to collect, let's say, digital data, so also, I mean, oceanographic data, for example. It should be very lowered the kind of activity in order to start reporting the data. I mean, we discussed a bit during the day that in order to involve people, we need to simplify the activity and the data submission system and management system in general. So it's quite important. And then, of course, also, we have to identify technologies that are very easy to be deployed. The example before is very nice, because then it means that each and every one really can start using things, scanning a QR code to register the sensor, and then just putting the system on top of the boat, and then you go. And then you know that you are contributing to the general picture. Yes, we need to work all together in order to make more consensus on the way we are using the data. So we need to start working with this data. We need to identify, we need more sensor, we need to identify more action. And I'm mentioning the Landsat project because it's quite important for the people that knows new technologies, because we are building up a sort of a reserve list of low-cost technologies, because the project has allocated some money to purchase these technologies. So please come in contact with us, because we are making this list and we can really start using new technologies, low-cost technologies. Next steps, this is my last slide. We are also thinking about to set up a sort of focal point for coordination, because as we saw, we have different initiatives. Some can be grouped, some other are not really fitting the puzzle that we are developing. And then, of course, it's quite important to have a key place in which people can ask and have direction in order to select, which citizen science project contribute to, or which kind of technology they can deploy. So it's really making the network. So please help us in doing that. We have many logos and people and projects that are already working on that. But of course, again, it's a quite important activity, a community-based activity that we have to do together in order to support the fair access to this very powerful and amazing new kind of data. Thank you so much.
Thank you, Antonio. Is there any question?
No
question? Yes, there is.
Yes, thank you. That was a very interesting talk. I'm wondering, you're talking about citizen science. Would you also consider working together with, for instance, fishing industry members who also consider putting sensors on board on their vessels? Not just for their fishing pleasure, but also for scientific use.
Well, yes, that community is a very good example of potential citizen science that can contribute, because, according to the definition, we say that a citizen science is someone that is doing a different job, but while doing that job is also collecting data. So fishing industry could be one potential target to target, yes.
Okay.
The Fishing for Data initiative?
Yes, we did. We did a couple of webinars for Fishing for Data, yes.
Yes. There are some interested fishermen now. I'll pass them on to you.
Yeah, but again, one point, and that is also important, having some side projects that are supporting this networking activity. Lancelot is helping in order to creating, I would say, this kind of primary hub for getting information and be directed towards solution and stuff like that. So it could be also let's say, the first entry point to start interacting with this kind of community and define together which kind of solution we can deploy. And we can take, for example, the soup solutions and so on. Yeah.
Hi. I'm here. I just wanted to make 2 comments. One is that the mission Starfish was not approved. So that 20% is a target to aspire to, because it's not been approved, and it's Mission Ocean what's in place.
Yeah.
And I wanted to add just a biology perspective for the citizen science, which we add another level of complexity, which is identifying what's being observed by a taxonomist or an expert, which you don't need if you have a sensor measuring temperature. For the biodiversity citizen science, you then have to add another layer of human resources, which is not easily available at most times.
We have examples where they do it. In Spain, for instance.
Yeah, we have examples.
You
but
have
it's,
examples?
But what Antonio was saying is not just the data, it's the quality of the data.
Yes, that is one concern. But again, if we go back also to some of the presentation that we had this morning, somehow we also are starting having tools that can support in that. Because if we think about machine learning approaches,
yes, but you always need a person.
But it's, yes, of course, it's all of, of course.
You can't get away with it.
You start having all the pieces of the puzzle.
Yeah.
I think that's generally speaking, you need some education, some guidance, some support. You cannot simply say, here's the tool and go away and you deliver high quality data. I don't think it works like this. You need some coaching. And anyway. But okay, hey, thank you very much.
Thank you.
We're going to the last presentation of this block. And that's John Mitchell. It's not Joni Mitchell, but John Mitchell. Okay. So he's going to sing Sharing How Data and Evidence Underpins the UK Leading Role in Offshore Wind to Enable Net Zero Energy Security and Nature Recovery. I had to read the sentence a couple of times. Next time you have to make a shorter title. Make a shorter title next one, because this one is different to catch on. But we'll listen, of course.
Amazing. Everyone hear me? Hi everyone, my name is actually Johnny Mitchell, that's what everyone calls me, so Johnny, close enough. I'm here in place of Chelsea Bradbury. She made up the title, not me, I'm getting in that in there now as well. And I'm a marine data manager at the Crown Estate, and I'm here to talk about how marine data can enable net zero and nature recovery in the UK. So I'm very aware this is the last slot of the day, you're all out of caffeine and sugar. You're probably not going to be very awake. This isn't going to be that technical. I'm going to spin a bit of a yarn and hopefully it will be interesting for you. So I'm going to start by talking, sort of setting the scene, introduce the Crown Estate and our strategy and our role in the UK and England, Wales and Northern Ireland. I'll then introduce the Marine Data Exchange and go on about how we've got industry data being utilised and used in projects that are impacting sort of net zero and that sort of thing, and then briefly point towards the future. So, what is the current situation on the seabed in England, Wales and Northern Ireland? So the map on screen shows the sort of assets that the Crown Estate leases for. So this is offshore wind, cables, carbon storage, aggregates and pipelines. This looks pretty busy, right, already? Well, if you overlay stuff like marine protected areas, shipping channels, defence zones, visual impact assessment areas, you end up with a map that really, really highlights just how busy and constrained the UK seabed already is. And this doesn't even have priority fishing areas on it either. So there's a lot going on out there, as I know you're all aware. However, we're in a world that, while it is already incredibly busy, we're going to need to utilise even more of it if we're going to get to net zero. So net zero targets are driving the push for energy infrastructure offshore. Achieving net zero implies something like 75 to 115 gigawatts of offshore wind in the UK alone. For context, we're only at 15 gigawatts at the moment. And we're going to need transmission cables, interconnectors, CCUS and tidal energy. And this all means that seabed demand is probably going to increase something like by 10 times out to 2050. We're also, again, as you're all aware, we're in a marine biodiversity crisis as well, and we really need to act fast to protect and restore biodiversity. So habitat protection is key to the UK government's 25-year environment plan. That's 30 by 30 to everyone. But as the seabed gets more crowded, and leasing and licensing and development choices are going to have more and more impact. However, there are definitely major opportunities to enhance nature as well, co-location, direct investment into nature, that sort of thing. And lastly, one of the things that is preventing some of the work to get to net zero and nature recovery is we need more visibility and coordinated actions to gain funding that is required to reach net zero and nature recovery. So we've got constraints around offshore energy grids and supply chains. We don't have a direct mechanism for investment into nature as well. So all the problems that here, all of this is the responsibility of a wide range of government bodies, agencies, and seabed user groups in the UK. And there isn't really convening power to bring everyone together. And this is where the Crown Estate sort of comes in. We are a slightly odd business. We're an independent commercial business established by an Act of Parliament in 1961, and we manage the seabed around England, Wales, and Northern Ireland, not Scotland. That's very important to get in there. We return all of our net revenue profit to the UK Treasury, but importantly, we have a purpose that allows us to think in the long term. Our purpose is to create lasting and shared prosperity for the nation, and we view this through the prism of environmental, social, and financial value. So as the custodian of the marine environment in the UK, as the people who are leasing the seabed, we lead on sustainable development, balancing protecting the seabed with the creation of lasting value. We have some core capabilities. We look across all sectors. We can bring people together. We have a strong convening power, and as I've said, we can look in the long term. And our strategic priorities are as follows. We want a thriving marine environment, an optimized and productive seabed, and a UK that is catalyzed towards a net zero future. These are not short-term goals, and they cannot be achieved in isolation. And to really achieve these, we need high-quality data and the insights that we can draw from it. And this is why I'm here today, because we do play a role in marine data and evidence in the UK. We work alongside our customers and stakeholders. We lead and fund programs that not only identify and address evidence gaps, but also challenge the status quo and drive positive change. Currently, we're driving forward the Marine Data Exchange, which is very much why I'm here at IMDIS, our survey data platform. We also have the Offshore Wind Evidence and Change Programme, which is a Crown Estate funded programme of work that will create a new shared data and evidence base that can be used to shape the future of offshore wind and the marine environment. We also have a Whole of Seabed programme. This is pioneering work to digitally map the seabed space needed to meet for future demand for a wide range of industries, infrastructure, and habitats out to 2050. So outputs from these programs can provide an evidence base to better understand engineering, consenting, and environmental challenges, while fostering collaborations between academia, government, industry, and environmental groups, trying to come up with positive solutions together. So I've briefly mentioned the Marine Data Exchange just now. I'm going to talk a little bit more about that now. So this is our offshore industry survey data platform, and it was set up in 2013, and data is acquired through what we describe as the data clause, which is a contractual obligation within all of the Crown Estate's project leases. The survey database holds over 280 terabytes of multidisciplinary survey data, and this amounts to something like 3,000 surveys, research outputs, and studies. 60% of this data is publicly available, and excitingly, this MDE also now covers the whole of the UK again, because Scotland have come back on board as of this May, which is quite exciting for us. We're also affiliated with Medin. We're a sponsor of Medin, and we utilise all of their metadata standards and data guidelines as part of our QA processes. So an industry data portal with publicly available data is not the most common thing. So I thought I'd share a little bit about how we've made this work. So firstly, we've worked really closely with industry, aiming to improve their experience, reduce effort, and speed up delivery and response times for getting data uploaded to our portal. We've also picked something of a middle ground on standardization. I'm going to go into the positives and negatives of that in a sec, but we ask for survey data to be compliant with the relevant Medin data guidelines, but don't ask for specific formats or file types. This is positives and negatives. It reduces barriers in terms of time and cost of delivery of data, but has led to a data holding that's not fully standardized, and thus is harder to draw insights from. However, it has meant we've received buy-in from industry. They're happy to provide the data to us. We also, as I mentioned, 60% of our database is publicly available. We have a confidentiality process to ensure that we get the data in so it doesn't get lost. So our confidentiality process is based on dialogue. The data clause is quite broad and allows us to adapt and evolve our approach as sectors develop, and we can address any concerns where they arise. Where concerns are raised and adaptation occurs, these can then be applied across all projects. Lastly, is something I want to focus on here, is that in the first 8 years of the MDE, we've really focused on the acquisition of data, simply getting it in through the door. a lot of our data comes from offshore wind in the UK, and this actually started 10 years prior to the Marine Data Exchange coming into existence. So we've been playing catch up for a lot of the last 10 years. But we're really trying to refocus on FAIR now, FAIR data, as everyone's been saying at this conference. As a result, over the last 2 years, we've really focused on improving our user experience, as well as improving the findability and reusability of our data. So we've been able to develop this industry data platform. How is some of this data being used? I've split this into some of the key areas against the Crown Estate's priorities. So firstly, some of the wind and geotechnical data that we hold on the MDE is being used to lower the cost of offshore wind. This is better informing developers around the levelized cost of energy, which reduces risks and costs on projects. We're also seeing a lot of the environmental data being used to understand and reduce the impact of offshore wind in other sectors, such as within the Poseidon programme, which aims to produce a nationwide marine environmental baseline in the UK. This is through a synthesis of newly collected and reused data. A lot of the environmental data from the MDE is also being used in a number of eco-wind projects, which explore the ecological consequences of offshore wind, and of course multiple PhDs as well. We've also been able to feed into work helping to speed up the deployment of offshore renewables too, reducing project development timelines through feeding data into platforms like One Benthic, which is run by CFAS in the UK, and also IC's Joint Station Data Programme as well. We're also handing it, 1 minute, I better hurry up. We're also feeding into projects such as Nature Inclusive Cable Enhancement Programme, and we're also seeing multiple developers use the data to speed up the deployment of offshore wind. I will skip through this bit because I'm very aware that I'm about to run out of time, but this is sort of our ideal cycle. I'm sure this will be very familiar to many of you, and you can probably replace the Marine Data Exchange with any number of data repositories here. But we really want to see data feeding into net zero nature restoration projects directly, but also furthering research and evidence. This can allow us to develop our evidence base for the whole of seabed programme, allowing us to enable that route map out to 2050, which allows us to predict where some of the stuff is going on the seabed, while also identifying gaps that can be resolved via more data collection. Where next for the Marine Data Exchange? Well, we think there's a number of bits that we can do to help enable these efforts. Firstly, there's a number of areas, but PDF data extraction will be really key. We receive a lot of industry data reports, and we want to crack these and allow us to enrich our metadata quickly and easily using machine learning. Along with this, we want to use some of this information to inform an internal large language model chat to aid some of the accessibility and understanding. We're also doing a bit of work in APIs. I know this isn't groundbreaking, but we really want to make our metadata at very least available via API, and then make some of our more structured data types like AGS, geotechnical data, available. We're also looking to try and reduce some of the cost and carbon of storing our data via some of Microsoft Azure's storage options. So, in summary, TC, custodian of the marine environment in England, Wales and Northern Ireland. We play a role in the UK marine data space, and we like to think that the MDE demonstrates how industry data can be collected and utilised to enable the transition to net zero and nature recovery. We really want to ensure this continues and this data can benefit all and continues to be reused. Thank you everyone for listening. Any questions from anybody?
Very interesting talk. We enjoy it. I only one question. When the information you get from the companies, you're using all of it, or you're just taking part of it? I mean, it's how you are dealing with I mean, you work with companies. I guess there's some private thing and some public thing. So how are you dealing with that? Can you tell us something about that?
Yeah, so we bring in sort of only the primary survey data from the companies. So that initial, say you're doing a geophysical survey for an offshore wind farm, we'll only ask for that initial survey report. We're not going to get into engineering design or anything like that, technical elements related to turbine design or anything like that. We sort of do a hard line there to ensure that they're happy to provide the data to us.
Thank you. Really nice put together. How do you balance the fundamentally different data cultures between the different research communities? So I'm thinking of the biological community who lean towards closed data because there's never enough data, and the results they get, there's less certainty, versus the physics community, which tend to be more open by default. And there's a really challenging clash between those cultures sometimes. So do you have to balance that, and how do you do that?
That's a really good question. I'm not sure I have a definitive answer for you, but it's definitely a challenge. I mean, we're quite lucky in that the data that we bring in, we have a contractual obligation behind it. They have to provide it to us. But the timelines about some of the confidentiality of releasing that data shifts with sort of project stages, so that's one way we handle it. For a lot of industry, they're more concerned about the site characteristics, the geotechnical, the geophysical side of things, rather than the more environmental data. That's usually mandated by government to collect that. And strangely enough, they're normally more happy to release it. I think on the academic side, we don't hold a great deal of academic data, but there's definitely more concern there. And we try and take a bit of a flexible approach. The main thing is preserving this data and making it available when we can.
More? People like a question or not? No? John, then thank you very much. Very interesting. And I have now the task, let's say, before we stop here, let's say, to do a small summary. So I'll do my best, of course. But yeah, I think it was a very diversified program this afternoon. And we started with, in fact, the road from decentralized to central. That was, let's say, AMONET story by Connor. And that was followed by 2 presentations on AMONET biology by Joanna and AMONET chemistry, especially the handling of marine litter by Matteo. And then we had, in fact, 2 presentations of, let's say, a national data center. So one, of course, our man here, let's say, with, in effect, the Norwegian data center network, you would say, yeah? More than network, let's say, in 10 years, how you're evolving and all your connections. And also later we had Marcin, let's say, telling us about Ekudo in Poland, also having a national network, and how he mobilized, in fact, many institutes, let's say, under one heading. And that's, of course, we like to see this because that's the idea, let's say, make national networks. NODC is not a center as such, it's the core of a network, and they can help, let's say, to educate and train others in adopting standards, and this way share the data and make them ready for national use, regional use, European use and global use. So you know the story. Then we also had Hong Min, and she went a little bit into one of the projects, the Eurofleets Plus project, in which, let's say, we have an active so-called transnational access, so cruises, and then a follow-up to get the data, and also the learning curve from that project. Let's say how to deal with different data in different stages, and let's say very cooperative PIs and less cooperative PIs. But that's practice, of course. That's the normal practice of NODCs when they're working with scientists and scientific, because they have another objective. Let's say they want to make science. And then not always the first priority is to make the data sharing, but we make progress in this. That's for sure. Also, we saw the new Eurogoose data policy, and to summarize, let's say it's all: let's make the data more public, CC BY, and also do every effort, let's say, to share it as widely as possible, because it's especially for the essential ocean variables, and most of the data that they collect as Eurogoose is essential ocean variables. And then we had. Then we went to SOUP, and we also went to, let's say, to Linda, and we went to Antonio. And in fact, SOUP is a project, let's say, to work together with industry to develop more instrumentation, and also low-cost instrumentation, which then can be used for stimulating uptake by others from small to larger boats or platforms, let's say, to collect data and make it shareable, because it will be supported by a couple of, let's say, German institutes that really have the capacity to keep the data and make it ready for uptake. And Antonio was talking more about, say, the citizen science, also low-cost sensors, and also, of course, how to get more of these citizen science projects really get the investment, let's say, and educate people to get real good data out of this. And I think there's a learning curve, and the Commission is stimulating this, so there are many projects coming now in the EU domain which will follow up. And also, we see that there is a lot of interest, let's say, from the public, because also at schools and universities, people get more and more aware that the ocean is something we have to share, and they're interested, in fact, to contribute, let's say, to a better environment. And that's a message that you see slowly also in your own children, etc., and your grandchildren. Let's say they start accepting and adopting these principles, and that's very interesting. And we have to, of course, not to play with that, but we have to be ready for this. Let's and help them and educate them. And finally, we had John, and he was talking about, let's say, the Crown Estate and the Marine Data Exchange. And the only thing you didn't tell, John, was that we are almost on the edge, let's say, of releasing the coupling of the Marine Data Exchange to MEDIN to AWNet ingestion. Of course, that's one of the links that we are doing. Let's say that the Marine Data Exchange has I would say, a wealth of data, but also documentation, and we are looking for the data. And we have an arrangement now that MEDIN, they select interesting data sets, more and more. They make them ready in the MEDIN network, and from the MEDIN network we are almost ready with the bridge, let's say, to AWNet ingestion, by which also the data becomes part of AWNet. And that's, we are very happy with this relation. And I also understood from my colleagues that you still have to work a little bit on the licensing, let's say, to get the CC BY, because in AWNet we only take CC BY 4.0, but that's a common, let's say, a common challenge for you and also our established colleagues from the UK, Leslie Rickards over there. She has been very active in this domain. Okay, but now I stop kidding, guys. It was a very interesting program, I would say, this afternoon. I hope you all enjoyed. And still, I'm still amazed by the fact that we have such a full room, because it makes me really happy. And I hope that tonight our big leader is here. He will tell us all about will tell us about this night. And tomorrow is another day. Okay, so go ahead, man.
Thank you. Well, I just have a short message. They popped me a question a couple of weeks ago. Do you want a 3-course menu or a 4-course menu? And I said, I don't understand the question. So there will be a potato and leek soup soon on, followed by a carpaccio of scallops. And then on the second page, there are roasted veal fillet for main course. And then you have chocolate mousse for dessert. So if you show up here at 20:30, 8:30, in this room, hopefully it's a bit more cozy than now. Dinner will be here. Yep. And the only thing we have to do now is to clear the room. Instead of getting everybody in, you will now be thrown out. Take all your belongings. They will start redecorating the room. Thank you.